Thank you, Mr. Pythoholic, for such a boring introduction to such an interesting topic. So AWS Serverless actually consists of multiple services that enable us to build and run serverless applications by providing us with fully managed services which do not require us to provision, maintain, and administer servers for backend components. So which for now may not be important to the user, but they play a huge role in the lives of the developers and the architects. These components can be like your compute, database, storage, stream processing, and message queues. And before getting into all these complicated terms, we first need to start from the basics. So let's start off with our basic understanding of what is serverless and why has everyone inclined towards designing serverless applications or serverless architectures. So now if I ask you to design an application from scratch, and if I give you a hefty budget and I ask you to take your own ideas to design this application, host it and make it available to the users, you will have a very straightforward approach if it's with an on-premise solution. And here, when I'm talking about application hosting, it is in the perspective of giving you a very simple example. So please don't get emotional or sensitive. This is just an example. Okay, so there are surely multiple ways to do it, but this is a very simple example that I wanted to give. So let's see the example here. So when it comes to our application hosting, you have your application servers, and along with that, you would need your developers to develop your application that you want to host on the server. And there comes a very important point. You will need computation resources, you will need memory and storage space, and to align your application to be accessed across the public facing or private facing interfaces, you would need your networking blocks. And all these things that are mentioned here need, first, your developers to develop the application. Secondly, you have to provision the resources based on the demand of the application with obviously your vision of how much traffic you're going to expect or how much traffic you are expecting to have. And you need to spare resources to provision database, the deployment of the database and maintenance of it, and other local storage to store your application data. And you will have your networking team to provide the subnets needed to host your application. And all these will have so many overheads. And that is why moving to the cloud is now considered to be a better approach. But having said that, we also know that we can have a hybrid architecture as well. I know you might be ready to put that in the comments section as well, and I totally agree with you. But for now, so I just want to tell you that, so just for us to be in context, just think of two ways, one with the on-premise and one with the cloud. Okay, so now let's see the approach with AWS. So when we move to a cloud-based architecture, we move from the conventional ways of provisioning resources. First, that will remain common between all the architectures is that your developers have to develop the application. You have to write the code. That is the basic first step, isn't it? Secondly, you have to provision the resources based on the demand of your application and your vision of how much traffic you are expecting to have. So instead of doing it manually in AWS, what you can do, you can attach auto-scaling groups to scale instances, and those instances and their capacity and performance can be done over the cloud as well. That's what makes the cloud very convenient, isn't it? Next, you need to provision database, which on AWS you can host on your own EC2 instances. And I'm not commenting on how you deploy it, as you all are very well aware of it by now. And you are free of the maintenance and other local storage to store your application data, because it comes attached to it based on the configuration that you provide. And with security groups, you can handle the network traffic, and you can as well attach it behind the elastic load balancer to host your application's request and the traffic. All these features that you see here started a movement for easier and effective application deployment. But there were overheads here as well that was related to its deployment and management of your own resources and how you want to handle them. But what if your idea of hosting application revolved only around how effective and imperative your time is that you spent for the deployment? Now you wanted to remove that overhead from your architecture, where you had the need to just think of your application itself and not how you want to provision servers or resources around it, isn't it? That's a very good point, and that's a very valid point. And that's where the idea originated for a cloud service provider managed serverless infrastructure, where you just had to worry about the application or the product at hand and not the servers. With serverless, You need to bring your own code or application, and you don't have to worry about the application hosting. You will be provided with the computational resources that you need to create a productive application with high availability and power that it needs to serve its consumers. And with this, you and your consumers will be satisfied. And that's what it means to be serverless. Serverless doesn't mean that there are no servers, or serverless doesn't mean that there are less number of servers. It means that you don't have to worry about the servers or how to manage them. You need high performance, you will get it. You need high availability, you will get it. You need an API gateway, you will get it. And you need a robust database, surely you will get it. And the biggest advantage that you have with this is that you will have a lower cost of ownership, because you don't have to structure the servers, and the time that you use to spend on designing these architectures and maintaining these servers, you can put that precious time on making your applications better. And please don't get confused when I'm talking about maintaining servers. I am actually talking about the application deployment itself, and I'm not talking about patching or the things that AWS does to manage its servers. I'm sure you can relate to it, and I'm sure you can relate to what I'm explaining here as well. So if I have to reiterate it once again, so the biggest advantage that you have with this is that you will have a lower cost of ownership, because you don't have to structure the servers, and the time you used to spend on designing these architectures and maintaining these servers, you can put that precious time on making your applications better. Okay, so I hope that was clear. Let's move on. So now that we have discussed the way we reached the stage in computing with serverless, let's talk about some pointers with serverless. And let's do some introspection on these two things. So first off, let's talk about what is serverless. So what AWS tells us is that serverless is the native architecture of the cloud that enables you to shift more of your operational responsibilities. Remember, shift more of your operational responsibilities to AWS, increasing your agility and innovation. Can I ask you something? Are you aware of what is a native architecture? If not, don't worry, it's very simple. So native architecture is a design principle which is used to design applications and services which are built specifically to exist in the cloud, like microservices, isn't it? So I hope you remember that I told you that time that to just think of either an on-premise solution or cloud-based solution. And we also had an argument about hybrid architecture as well. So you can come out of that and think of the overheads of using the default deployment steps we follow when we use AWS Cloud. With this, you can shift some of your resources that you used to manage before to serverless and use it more effectively. Like shifting your EC2 hosted database to a serverless Aurora database or a Dynamo database, like shifting your EC2 computation to AWS Lambda, and like shifting your data stores from local storage to AWS Simple Storage Service, that is S3. And this eliminates infrastructure management tasks such as server or cluster provisioning, patching, operating system maintenance, and capacity provisioning. And you will get everything that is required to scale and run your application with high availability. So that's one less thing to worry about. And next thing that we have here is why use serverless. So as I've already mentioned before, with serverless, you need to bring your code or application, and you don't have to worry about the application hosting. You will be provided with the computational resources that you need to create a productive application with high availability and the power that it needs to serve its customers' requests. And as AWS tells us, serverless enables you to build modern applications with increased agility and lower cost of ownership, or lower total cost of ownership. With this reduced overhead, it lets your developers get more time and energy, which in turn can be spent on developing reliable applications. And the following can be termed as the pillars of modern applications. So first one is the faster to market. So it means that it reaches your customers on time, because you can spend more time now designing productive applications rather than thinking about the overheads of maintaining the servers. The second one is increased innovation. So it obviously means like you get more time to innovate. And the third one is improved reliability. And the fourth one is reduced cost. I think this we have already discussed. And all these make up for a serverless architecture. So with the evolution of AWS serverless, it was first initially restricted to serverless compute, that is by using AWS Lambda. I know all of you might be aware of AWS Lambda. If you don't know, then it's just fine. But now AWS has spanned it across multiple services and across multiple domains like compute, storage, data stores, API proxy, application integration, orchestration, and analytics as well. And these servers are very interesting to learn, so we might discuss some of them in depth, and others which are more conceptual, we will discuss them in brief. So if you see here, for compute, we have AWS Lambda, Lambda at Edge, and AWS Fargate. So don't worry about them. If you aren't aware of them, we will discuss them one by one. So for storage, we have AWS S3 and AWS EFS. And for data storage, we have AWS DynamoDB, AWS or Aurora Database, AWS RDS Proxy. And for API proxy, we have API Gateway. For application integration, we have AWS SNS, SQS, AppSync, and AWS Event Bridge. For orchestration analytics, we have AWS Step Functions, Kinesis, and AWS Athena. And most of these we have already covered. So the green ticks that you see here, we have covered most of the services that we wanted to cover in serverless before itself, but most of the important services are still there and we will cover them one by one. So don't worry about them. And along with AWS Serverless Computation, we also have AWS Serverless Developer Tools. For the serverless framework, we have AWS SAM, which is also known as AWS Serverless Application Model. And for continuous integration and deployment, we have AWS CodeStar, AWS Code Pipeline, AWS Code Deploy, and AWS Code Build. And for monitoring, logging, and diagnostics, we have AWS CloudWatch and AWS X-Ray. And at last, for authoring and development, we have AWS Cloud9 and AWS SAM CLI. So that is basically your AWS Serverless Application Model CLI. Now tell me, do you have your concepts cleared on the line mentioned here? Build and run applications without thinking about servers? That's the whole gist of being serverless. You have to just focus on building a resilient application and the rest will be handled by the cloud provider. Okay. So now let's do some recap on serverless capabilities. The first one we have is no server management. So rest assured, you don't have to provision or maintain any servers. And second one we have is pay for value. So it's a very interesting term, pay for value. Remember that. So this is a very important point and everyone must be aware of this, is that the whole glory about serverless has a caveat that boils down to the cost. Remember that you have to pay for consistent throughput and execution duration rather than by the server unit itself. So you only pay for the request transaction and AWS charges you for only that and not for the server usage itself. Remember that. Okay, for every transaction that you make or every consistent throughput or execution that you make, you will be charged for that itself. And the third one we have is flexible scaling. So when it comes to performance of your application can be scaled automatically or by adjusting its capacity through toggling the units of consumption rather than the units of individual servers. It means that with the increased demand or traffic, it will automatically scale and it can scale up or down based on the requirement. Automated high availability is self-explanatory that it is automated high availability. So when you use serverless computation, it provides built-in availability and fault tolerance. So if there is any easy failure also, you'll not get to notice about that. And that's the very good part, I think, isn't it? So in today's session, we will be discussing about what is AWS Lambda, what is the need for using AWS Lambda, and we'll also see the differences between AWS EC2 and AWS Lambda. We will check out some of the trigger points that we have for AWS Lambda, that is the AWS Lambda trigger points, and we'll also see some of the features for AWS Lambda, and we'll also have some mathematical calculations that we will do for the pricing model that we have for AWS Lambda. And also in the next session, I'll also cover a very important topic, that is basically your concurrency models, where we'll cover both reserved and provisioned. And then at the end, we will discuss about architectures and designs for AWS Lambda. Okay. So as we are going to talk about serverless compute and deployment, let's check this real-time example. So your boss in a meeting came up with a new requirement where he wants you to deploy an application, and he said, "Hi, host an application which will be used as a simple reporting API service for our customer data and let me know once it's done." And you were fine with that. You said, "Sure boss, I will work on that as soon as possible and will update you once the service is up and running." So you went ahead and wrote your API code, and your first thought was to deploy it on an EC2 instance because you have been doing it for a long time while hosting applications. And to host it on EC2, you had to go through these steps. So you had to choose the VPC, then you had to choose the AMI for the purpose, choose the right processing unit, choose subnets to maintain high availability, then choose the storage, and then attach the security group, and ultimately you had to deploy the code that you have. Then you took a pause and you realized that you still have a lot to do. So you went ahead and created the launch templates. You then created the auto scaling groups. Then for the load balancers, you created the ALB. And then for the storage, you created the deployment for the database. And finally, you succeeded in creating the deployment. Finally, you came up to your boss and you were happy to share this information. Hi boss, we are done. I have hosted the application and we can make use of it. And you said you had deployed it with an EC2 instance with auto scaling. Your boss went ahead and rejected this, saying, "This is not feasible. It's just a simple report generator. Do you want us to spend this amount of time in future as well, managing these servers for a single service, which will be used in short spans?" There was nothing wrong with the product and the API service. The users would still be able to make use of the service, but the thing that would get affected is the efficiency of the platform and the infrastructure maintenance. The amount of time that we would spend in maintaining the instances and the deployments for a small or simple one-directional API service would be fairly laborious, which would not be a feasible option in the longer run due to the operational overheads. And that's where AWS Lambda came into the picture. So you went ahead and switched things around by moving on with the serverless approach. You started off by deploying your code, which is an API service written in Python, by creating a Lambda function, by providing the required memory for its processing. For the report files, you attached an Amazon S3 bucket where you planned to store your report files. For table entries and the inventory and the user data, you moved ahead and attached a DynamoDB, which is a serverless NoSQL database. And for your API trigger point, you went with the reverse proxy service API gateway, which we will be discussing in the upcoming sessions as well. For now, just remember that API gateway is a service provided by AWS, which helps us to create an entry point for the backend services and which sits between your clients and the services you host. So now the users are happy and they are able to connect to the API, and your boss surely appreciates the design. But you might ask me, what did we achieve by switching our application hosting to AWS Lambda, which was already hosted on EC2 instances, and why we moved to a serverless architecture? That is the reason we are here. So let's see what we can achieve with EC2 and what makes it different than Lambda, and why we went ahead of using Lambda and not EC2. So when it comes to EC2, the basic idea is to create a VM, that is the virtual machine, so that you can use it anytime that you want. But the problem is that it has to be running all the times, even if there is no traffic at all. But here we are not trying to defame EC2 instances, because EC2 is powerful in its own rights. And most of all, let's check these points. If you wish to go in depth, you can read more about this in the documentation as well. So we mostly recommend using EC2 instances if you want to host a complex multi-purpose website, or if you are hosting and testing with multi-purpose processing powers for various use cases, or when you need consistent high performance computing, or when you have the need to create pre-configured images or customized AMIs. On the other hand, Lambda is a very short and simple multi-utility serverless service, but without a doubt, it's a very powerful one as well. So when we compare it with EC2 in AWS Lambda, we don't have to launch any virtual machines to host our code. And that would be the most basic difference, as its rightful name comes from being a serverless computing powerhouse. But for now, let's talk about some of the pointers here as well. If we want to host short compute time modules, or if we want to provide a function as a service using AWS Lambda functions, of course, or if we want to provide a compute power for simple task automation, or if you want to have a provision for real-time log analysis, and henceforth. So these are a few differences that make AWS Lambda very useful when it comes to compute optimization. I know you guys might be thinking of so many other reasons, but don't worry, till the end of this session we would have already covered them as well. but I felt it was the right decision for me to clear some of them right now. Now let's come back to the actual topic and let's discuss at length about AWS Lambda. So as per AWS Lambda lets you run code without provisioning or managing service, and you pay only for the compute time you consume. So here you don't have the need to launch virtual machines and keep them running all the time, and you pay for the compute time only. I hope you remember the previous session we already discussed about serverless and why we associate the use case with this term called serverless. If you haven't, then I would request you to please check the video out. Link is in the I button above on the top right corner. As I've already mentioned before, with serverless, you need to bring your code or application, and you don't have to worry about the application hosting, and you will be provided with the computational resources that you need to create a productive application with obviously a high availability and the power that it needs to serve its consumers' requests. So when I say AWS Lambda lets you run code without provisioning or managing servers, and you pay only for the compute time you consume, what it means is that you can run code for virtually any type of application or backend service, and you don't need any administration of these servers. You have to just write the code that you want on the Lambda editor, or if you want, you can upload your code to AWS Lambda, and Lambda will take care of everything required, or what we rightly call as resource provisioning, to run and scale the code that you have, and in turn it will also provide high availability. And the best part about this is that AWS Lambda, you can set up your code to automatically trigger from other AWS services or call it directly from any mobile or web application. That gives you the power to get the results from anywhere you want. So there are a few important features of AWS Lambda that we have to discuss. First off is no servers to manage, and AWS Lambda automatically runs your code without requiring you to provision or manage servers. I think this is quite evident now that you don't need to create or provision or manage any servers to run your code, and you can just post your code on the AWS Lambda and run them using any trigger point. The second one is continuous scaling. So for continuous scaling, AWS Lambda automatically scales your applications by running code in response to the trigger. So let's suppose you have a lot of users using your service, and in that case your code can run in parallel and each trigger will be processed individually. That's a very big thing. The trigger means an API call or execution, like for example you send a GET request or a POST request to perform a call using an HTTP request, and the scaling will be done automatically based on the size of the workload. The third one is sub-second metering. So sub-second metering means like charging you for a unit of work or operation. So with AWS Lambda you are charged for every 100 millisecond your code executes and the number of times your code is triggered. So you are charged for the unit of work that you perform. The last one is consistent performance. So whenever we host the service, we try and estimate the amount of processing power that it might need, isn't it? And based on which we provide the resource. Here with AWS Lambda, you can optimize your code execution time by choosing the right memory size for your function. And you also get the option for provision concurrency to keep the response time within double-digit milliseconds. Don't worry, we'll discuss about this in a short time. So now let's check the visualization here. So here it's a very simplified way to look at the workflow with AWS Lambda. First off, you write the code that can be your service API, or you can upload it to AWS Lambda, and then you create a trigger point that kicks off the Lambda code that you have and the code execution using a static website that is hosted on the AWS S3 or any trigger point that you have, which in turn triggers the function that's hosted or written into using AWS Lambda, and upon execution you get the result back and you are charged only for the compute time, or what we can also phrase it as the duration of time it takes to execute the code. So you write the code, upload it to Lambda, then execute your code with a trigger point and get charged for the compute time. I know you might be thinking I'm speaking a lot about trigger points and so on, and what are these trigger points? So trigger points are the ways you can call your Lambda code. So don't worry, that's what we'll be discussing next. I hope this was clear. Let's move on. So there are several ways with which you can trigger AWS Lambda, and let's discuss them one by one. So I'm sure you are aware of what is the difference between synchronous and asynchronous calls. I hope you are. So the first one is synchronous invokes. So here your function executes immediately when you perform the Lambda invoke API call. So it's a synchronous call where you don't have to wait or poll for the response to come at a later stage of time. Okay, so among them we have services with which we can trigger AWS Lambda. So here we have Elastic Load Balancers, or Amazon Cognito, Amazon Lex, Amazon Alexa, Amazon API Gateway, Amazon Cloudfront, that is Lambda at the edge, and Amazon Kinesis Data Firehose. Okay, so next off we have for asynchronous invokes. So here it places the invoke requests in AWS service queues and processes these requests as they arrive. So we have services with which we can trigger AWS Lambda for asynchronous invokes. So they are AWS Simple Storage Service, or AWS S3, or Amazon Simple Notification Service, or Amazon Simple Email Service, and AWS CloudFormation, AWS CloudWatch Logs, AWS CloudWatch Events, AWS Code Commit, and AWS Config. And apart from these two, we have another one which is poll based invoke. Here Lambda will poll the following services on your behalf, retrieve record, and invoke your functions. So here we have Amazon Kinesis, Amazon SQS, and Amazon DynamoDB Stream. And let's check the language support that we have for AWS Lambda. It's a very good thing that we have a lot of languages that we can use to write AWS functions. So it starts off with Java. You can have support for Golang, a PowerShell, a Node.js, C#, Python, and Ruby code as well. And for the relational database, you will be given the support of RDS proxy, where you can make use of MySQL and Aurora databases. Okay, so I hope this was clear. Let's move on. So now let's understand the three trigger points that we already discussed carefully one by one. So the first one is the synchronous push, where we use the API gateway and trigger an API, that is product/data, and it executes the code present at Lambda. So this is a synchronous call or a synchronous push. Okay, so when you summon the API by sending an HTTP request, you get the response, and that's how the synchronous push works. So the second one is an asynchronous event, where you can push the request event to SNS or SQS messages to modify or perform operations on the website hosted at S3 or the file hosted at S3, and each of these messages are pushed to an event, and these requests will be executed when it is received by AWS Lambda. And the same concept is followed the way we saw with SQS. Okay, so the third one is poll based, where you can see we have the Lambda polling for the changes from the Kinesis data streams, which is stored in the AWS DynamoDB, and once it receives the data, it will be processed by the AWS Lambda. So as you can see, we have the AWS Lambda polling the data streams from the Kinesis, and which in turn pulls it from the DynamoDB, and based on that, once it receives the data, it actually performs the operation. I hope it was clear. Let's move on. So now let's check some of the features of AWS Lambda, and these points might seem to be pretty lengthy, but they are very important. Okay, so you can create new backend services for your application that are triggered on demand using the API or the Lambda API or the custom API endpoints built using Amazon API Gateway, as we already discussed. And Lambda natively supports Java, Go, PowerShell, Node.js, C#, Python, and Ruby code, and provides a runtime API. And Lambda manages all the infrastructure to run your code on highly available fault-tolerant infrastructures. That's a very good point for people who just want to run the code and deploy services without taking the headache of managing servers. And Lambda has built-in fault tolerance, so you will never realize if there is any outage. And AWS Lambda invokes your code only when needed and automatically scales to support the rate of incoming requests, without requiring you to configure anything. Here with Lambda, you don't need to host your application with auto-scaling groups with CloudWatch metrics to determine the amount of load to make it scalable. And for people who are looking for any support for relational databases, here in AWS Lambda, RDS Proxy offers support for MySQL and Aurora. You can use RDS Proxy for your serverless applications. Next, we have the provision to use AWS EFS with the Amazon Elastic File System or AWS Lambda, and you can securely read, write, and persist large volumes of data at low latency at any time or at any scale. And with AWS Lambda at Edge, AWS Lambda can run your code across locations globally in response to Amazon Cloudfront events. This topic we'll be discussing in length in the next part of AWS Lambda. For now, you just need to remember that with AWS Lambda at Edge, you can run your code across regions and locations with Cloudfront. And you can also use step functions along with Lambda, and you can build stateful long-running processes for applications and backends. And what step function helps us is that it helps us to create event-driven workflows by creating a sequence of AWS Lambda functions and AWS services that can fit into a business process workflow. And when it comes to security, AWS Lambda allows your code to securely access other AWS services through its built-in AWS SDK and integration with the AWS Identity and Access Management, that's our IAM. So if suppose you want to access CloudWatch or S3 or any other service from your Lambda code, you can create an IAM policy for Lambda to allow access for these services. When it comes to pricing, with AWS Lambda, you pay for the execution duration rather than by the server unit. So what it means is that you don't pay for the servers because you don't host them. Then what will you be charged for? Obviously, it will be charged for the requests you made and the server usage per unit. Okay, here the benefit and equally important thing is remember that when you host your code in Lambda, you choose the amount of memory you want to allocate to your function, and AWS Lambda allocates proportional CPU power, network bandwidth, and disk I/O. So if you increase the memory, it will increase the processing power proportionately for your computation, and you will pay more as well. And that's what we will discuss next. So with AWS Lambda, it counts a request each time it starts executing in response to event notification, including test invokes from the console. And if you talk about the duration of compute, the duration is calculated from the time your code begins executing until it returns the result or otherwise terminates the request, which is rounded up to the nearest 100 millisecond. I won't explain you rounding up values in terms of maths, but it's simple. For example, if you have a value of 145, when rounding up to nearest 100, it comes closer to 100 than 200, isn't it? And 180, if you have the value 180, it moves closer to 200 than 100. So if you use it for 180 milliseconds, you will be charged for 200 milliseconds, which is the value that we have when we round it up to the nearest 100 milliseconds. Okay, so this was a simple mathematical calculation that you can also do. But here we are going to discuss about the pricing for AWS Lambda. So the price that you have will be charged on you depending on the amount of memory that you allocate for your function and the proportionate CPU power. As I've already told you, when you host your code on AWS Lambda, you choose the amount of memory that you want to allocate to your function, and AWS Lambda allocates proportionate CPU power, network bandwidth, and disk I/O. So if you increase the memory, it will increase the processing power proportionately for your consumption. And there is a very good thing for the free tier people here. So with AWS Lambda free tier usage, it includes 1 million free requests per month and 400,000 GB seconds of compute time per month. Here you might feel what kind of unit of measurement is GB seconds, and honestly it's a bit confusing as well, isn't it? But listen to me very carefully. So I've told you that you have to allocate memory to execute your code, and that can be like around like 500 MB or 1 GB or 2 GB. So GB second means the number of seconds of computing you have done multiplied by the number of GB of memory that compute allocates. So let's suppose you allocated 1 GB and it runs for 5 seconds. Then it's calculated as 5 GB seconds. Okay, and for the request, we have $0.20 per 1 million request. So it's like 15 rupees per 10 lakh requests. And duration of 0.000016667 for every GB second. So it's a very menial charge, but on a longer run, if you have millions of users, it will account to a very huge price. And just like banks, we have saving plans here that provide a flexible pricing model that offer low prices on EC2, Lambda, and Fargate usage. So we have two here. So the compute saving plan provides the most flexibility and helps us to reduce our cost for up to 66%. And for EC2 instance saving plans, so here EC2 instance saving plans provide the lowest price offering and the savings up to 72% in exchange for commitment to usage of individual instances, families in the region. Okay. For example, M5 usage in North Virginia. So these are the instances actually that will be used. Okay. So now that we have done the theoretical analysis of what is the pricing model, let's see a basic example for calculating the price of AWS Lambda usage. So let's take an example for AWS pricing, and let's take a case study. So you created a Lambda function, and let's suppose you allocated 512 MB of memory to your function and executed it 3 million times in 1 month, and it ran for 1 second each time. Your charges would be calculated as follows. So here I'm not trying to insinuate that you ran 3 million times equally divided across 30 days, but it's relative, isn't it? I hope you get the point. The first thing that we need to calculate is monthly compute charges. So the monthly compute charge price is 0.000, that's a 401667 per GB seconds, and the free tier provides 400,000 GB seconds. Remember, I'm not saying GB seconds as GB per seconds. I'm telling you that is GB seconds. So it's a multiplication. GB per second would be a division. Okay. So the total compute seconds is equal to 3 million requests multiplied by 1 second. That is 3 million seconds. So the total compute time that we have in seconds is 3 million times that it ran with 1 second each. So it is 3 million seconds. And the total compute GB second is basically your 3 million seconds multiplied by 512 MB, because you allocated 512 MB of memory to your function, by 1024, just to convert this into GB, 1.5 million GB seconds. So now the monthly billable compute GB second is your total compute minus free tier compute. Okay, so the total compute that we have is 1.5 million GB seconds minus the 400,000 free tier GBs that you get. Okay, so it comes around 1.1 million GB seconds. So now the monthly compute charges will be 1.1 million into the duration amount that we are charged for, that is your 0.401667 dollars. So it will come around 18.34. So this is the monthly compute charges. So how much you are asked to pay for the monthly computation. So this is the computation charge. Now there is the monthly request charge. Okay, so the monthly request charge price is 0.20 per 1 million requests, and the free tier actually provides 1 million requests per month. Okay, so this one, 1 million free requests per month. Okay, so the total request minus free tier request is monthly billable request. So the 3 million that you get, that you have assigned already, the 3 million time. So as it executed for 3 million times in 1 month, so the 3 million requests minus the 1 million free tier requests, so you get 2 monthly billable requests. So this is the actual spending that you have. So monthly request charges will be 2 million into 0.2 per million, so it is 0.40. So that is the request count. Now the total monthly charges will be monthly compute charges plus monthly request charges. So the total charges is 18.34 plus 0.40, that is 18.74. So if you allocated 512 MB of memory to your function, executed it for 3 million times in a month, and ran it for 1 second each time, you would be charged for 18.74. And this is actually relative to a particular region. So if you change the region, you will be charged in a different amount. So now that we have discussed the pricing model, let's design some applications. So here is a simple architecture for you using AWS Lambda that you can also implement. So the requirement for this product or the project is that we want to create a mobile application that helps you create and publish posts to your application, and that post should be published across all your friends list. Okay, don't think it is Facebook or something. We are completely reinventing the wheel by doing something new. Okay, so what we have to do here is we have to create the mobile application, and for the API REST service we use API gateway to make API calls to the backend service here, which helps us to execute our code by acting as a trigger point, and also helps us to authenticate and process API requests. And to execute our code, we are using AWS Lambda to write our API code, and whose task is to find out the list of friends you have. So we are using the code execution point or the trigger point as the API gateway, and to execute the code, the function that we use is AWS Lambda. So that was the whole purpose of using Lambda here. And that can be multiple messages that could be posted on the account. So for this, we are using AWS SNS to publish the messages onto the message broker so that it can be sent to all the users who are part of your friends list. And you can simply write your code that fetches the list of friends that you have using the AWS Lambda function rather than deploying and managing EC2 instances. So this is a pretty simple example or architecture of using AWS Lambda. So you write the application and you create a trigger point using API gateway, and that actually triggers your AWS Lambda functions, and whatever output or social media message that you have, gets published using the AWS SNS that actually propagates across your friends list in the media app, social media app. And as all of you wanted me to talk more about real-time examples and models, let's check one more design for a simple application using AWS Lambda. So the requirement of the product or the project is that you need to create a web application that could be accessed via desktop and also could be used in mobile application, which helps the user to get the stats of the cricketers and the teams for the users, which would be geolocation based. So let's suppose a user in London would be shown more about the cricketers of England cricket team, and similarly for a person staying in India, it would be shown for the players of Indian cricket team, obviously. So here what we have done is we have put our HTML static code in AWS S3 bucket, and when the application needs to communicate with the backend, it can send an API call to the API gateway. The data of the cricketers and teams are stored in the Dynamo database, and the logic for fetching the data as per the country or the location is hosted on the AWS Lambda function. And AWS Lambda fetches the data for the cricketers and the team by communicating the same with the AWS Dynamo DB, and it passes to the website to host dynamic content based on the user's location. So here what happens is whenever the user is in London or any part of the world, by using the API gateways, we are able to calculate or we are able to trigger the AWS Lambda function, which fetches information for the cricketers and the players which are close to that particular region, and that is what we are able to show to the user. And that actually gives us a sense of hosting dynamic website by using our front-end static code. Coming to the topic, I feel this is a very important concept which I think others ignore it, but not here. So let's start. With AWS Lambda, you can enable concurrency for the request that you want to provision. For this, AWS Lambda provides two types of concurrencies. One is reserved and the other one is provisioned. And we will discuss them one by one. And in AWS Lambda, in order to ensure that a function can always reach a certain level of concurrency, you can actually configure the function with reserved concurrencies. Okay, wait. You might ask me, what is concurrency? You have been talking about concurrency, but what it is? A good question. So before moving forward to reserve concurrency, let's talk about concurrency itself. So concurrency, I hope and I am requesting you to listen to this very carefully. Okay, so concurrency is the number of requests that your function is serving at any given time. I'll repeat that once again. Concurrency is the number of requests, or concurrencies are the number of requests that your function is serving at any given time. So Lambda has your function that you have written and uploaded, and if a single user makes a call to the function, it is considered to be a single request because it is a single call or single execution. So the number of requests that your function is serving at any given time, we consider that as concurrency. When you make a call and execute a Lambda function, AWS Lambda assigns or allocates an instance to it in order to process the request. And once the function execution finishes, it can handle another request. But wait, but you have to understand that it's not like it can only process one request at a time. You can have a parallel request running on AWS Lambda, which in turn will incur more memory requirements and initialization of multiple resources. And just like any other service, AWS Lambda is also bound to quota. So if you see the table here, the default quota for the concurrent requests is 1000, and it can be increased to a huge amount by getting support from AWS. For function and layer storage, we have 75 GB default quota, and for ENI per VPC, or what we call as Elastic Network Interface per VPC, you can assign a maximum of 250 as per the default quota limits. I know you might be feeling really confused, but listen to this very carefully. For a moment, imagine concurrency values to be a pool of numbers. Okay, for example, let's take it as 100. And if 100 is the total pool value, then all 100 when not reserved, it's considered to be unreserved. And if you assign 50 out of them to the function, then that 50 becomes reserved. And the other one, yes, it is free and unreserved. And when a function has reserved concurrency, no other function can use that concurrency. And for the other functions in that account, they have to use the unreserved space or the unreserved concurrency. So now as you have some kind of information regarding concurrency, let's move on. So as I've already told you, that concurrency is the number of requests that your function is serving at any given time. In order to ensure that a function can always reach a certain level of concurrency, we can actually configure the function with reserved concurrency. So as this term suggests as reserved, we must be clear that we are trying to reserve concurrency quota for a function for its efficiency or need. And with reserved concurrency, we have the following effects. One, where other functions can't prevent your functions from scaling, and the other one is that your function can't scale out of control because it has a limit on the concurrency to which it can scale. So if you see this image here, imagine the whole space to be a total concurrency, out of which the orange pattern that you see is the reserved concurrency. Okay. And the purple line that you see here is the throttling duration. By this, you can realize that when the function myFunctionDev throttles, it doesn't exceed the concurrency limits or the concurrency value. And the other functions which are running on the unreserved concurrency won't be able to prevent myFunctionDev from scaling. And only that function will be able to run with that reserved concurrency, as it's implied and that it has been reserved. So you might want to ask me, like, what are the problems and what could be the advantages of using reserved concurrency? So if you understand this concept very clearly, you have to comply that all the functions in the same region without reserved concurrency share the pool of unreserved concurrency. So let's suppose you have a limit of 10. Then the whole 10 represents the value of unreserved concurrency. Without reserved concurrency, other functions can use all of the available concurrency space. And this is a very bad thing because this will prevent your functions from scaling up when needed. On the other hand, if you feel your function will need this amount of traffic and it needs this space, you can provide it with reserved concurrency so that other functions don't interfere. Okay, so you have to be clear in your mind that you know that this function is going to need this amount of space. Ultimately, the problem might arise if most of the concurrency is reserved. Then the other pool of requests that you will have will face a higher latency if other functions take more time to set up and initialize. For example, there is a function that takes more time to initialize because the loading time of your function SDK and dependencies are higher. Other users who are trying to use the rest of the functions will face a lot of latency. And this is one of the main reasons why we have another type of concurrency in place, that is provision concurrency. So let's check that out. Next up, we have provision concurrency. You can enable provision concurrency for your Lambda functions for greater control over the performance of your serverless applications. That's what AWS tells us. And to mitigate the effects of reserved concurrency and to ensure that all requests are served by the initialized instances with very low latency, AWS Lambda provides us with provision concurrency. First, you need to understand that if there is a situation that arises that your functions need more power to handle increased concurrent executions and requests, you need to ensure that the users don't face low latency. And with reserved concurrency, it will surely limit your throttling if it exceeds your resource expansion. Then you will ask me how provision concurrency can help us with this. So listen to this very carefully. Lambda has a provision to integrate with application autoscaling. Yes, you heard it right. You can scale this service using application autoscaling. And you can manage autoscaling for provision concurrency by either of these options. So it can be based on scheduling, like you can schedule it to the scale when you need it, or you can scale it based on the utilization. The best thing is, for automated scaling, you can make use of the application autoscaling API to register a target and create a scaling policy. And you might have multiple questions to ask me, like how is it going to work? Will provision concurrency be set alone, or will it work along with reserved concurrency, or will it be both? And I would say yes, you are right. Provision concurrency counts towards a function's reserved concurrency and regional quotas. So it can be applied alongside the reserved concurrency that you have. And also it can be added up to the reserved concurrency of the function. And in this case, it will run all of the invocations in provision concurrency. So both of your questions are valid and the answers would be yes. So I hope it was clear. Let's check out the working principles here. If you see the example here, both the functions that you see here, my function dev and my function prod, both are running on provisioned concurrency and reserved concurrency. But the difference you can see is with my function dev. Okay, here my function dev is using the full pool of reserved concurrency and my function prod is with shared concurrency. And in the case of my function prod, the normal invocations are run with reserved concurrency, and in this case, if it needs additional throttling, it will run on provisioned concurrency. And on the other hand, the my function dev that you have here, all the invocations run on the provisioned concurrency. So you might ask me, I know you will ask me this in the comment section that, okay, you said all this, but what additional benefit we will get with this? And you also said that all invocations run on provision concurrency. How is that possible and what is the advantage of it? Because it is taking all of the space of the reserved concurrency and it is adding up the provisional concurrency there. So what is the advantage there? Yes, I understand your question. So wait and let me answer them in the next interesting topic. So let's check functional scaling with provision concurrency. So to start off with this, I want to tell you that with provision concurrency, you get a burst so that your users don't face high latency. So let's clear this first. That answers your second question. What if all the invocations run on provision concurrency? Okay, so that is basically because of the burst. You will get the burst immediately. So then you will ask me what will happen if the provision capacity also reaches its limit. So in this case, as shown in the example here, when the concurrency hasn't reached the limit, so when it hasn't reached the limit, AWS provides a burst, and if that also reaches the limit, it will scale up the function normally to handle any further requests. Okay, so with concurrency, you will have an initial burst of the traffic with regards to how much the function's cumulative concurrency in that region can reach. So at an initial level, it can reach from between 500 to 3000. And when the burst concurrency reaches its limit, the function starts to scale linearly. And if this concurrency isn't enough to serve all the requests, then additional requests are throttled and should be retired. But here as well, if your function still needs further throttling, then AWS tells us that we can provide you an auto scaling with provision capacity or provision concurrency as well. So yes, you heard it right. You can provide auto scaling to provision concurrency, as I have already mentioned before. In this case, what AWS means is that with application auto scaling, you can create a target tracking scaling policy that adjusts provision concurrency levels automatically based on the utilization matrix. So if you see in the example here as well, we see here that there is a range of minimum and maximum range of provision concurrency, and when the number of requests increases, autoscaling increases the provision concurrency in larger steps until it reaches the configured maximum concurrency. And when the request decreases, it moves on and lowers down the concurrency with smaller steps. Okay, these are the smaller steps and these are the larger steps. Okay, so it tries to create a balance for you and for your users as well. So I hope it was clear. And if you still have doubts, then please let me know. I'll try and create separate videos on specific topics as well. Okay, so let's move on. So now let's talk about the pricing for provision concurrency. So we need to understand that provision concurrency is calculated from the time you enable it on your function until it is disabled, rounded up to the nearest 5 minutes. Because I've already explained how nearest to 100 millisecond means, so you can check the previous video for that. So now we will take an example here as well. So let's assume you have allocated 1024 MB to your function and enable provision concurrency on it for 2 hours. So understand this, you allocated 1024 MB to your function and enable provision concurrency for 2 hours. The concurrency that you configured was 1000. You executed the function 1.2 million times during the 2 hours and it ran for 1 second each time. So the default values that you see here for provision concurrency for a particular region is 0.00, that is 5 zeros 41667 for every GB second. I hope you understand GB seconds by now. And the request that we have is $0.20 per 1 million requests. And for duration, the charges are 0.00509722 for every GB second. Okay, for request it is 0.20, and for duration it is 0.5097222 for every GB second. Okay, so now coming back. So the first thing is to calculate provision concurrency charges. So the provision concurrency price is 0.504167. Actually, we have rounded it up. Okay, for every GB second. And the total period of time for which provision concurrency is enabled in seconds is 2 hours. So 2 hours, when we convert it into seconds, is 7200 seconds. So then the total concurrency configured in GBs will be 1000 multiplied by, because 1000 actually is the term that we get, that the concurrency that you configured was 1000 multiplied by 1024 by 1024. So now the total concurrency configured will be in GBs, that is 1000 multiplied by 1024 MB, that is basically your allocated memory, by 1024 MB, that is basically we are trying to convert it into GB, so it will be 1000 GB. Okay, so total provision concurrency, which is amount to GB seconds, is basically your 1000 GB that you calculated here, total concurrency configured, multiplied by the number of seconds it has ran. So 1000 GB multiplied by 7200 seconds is 7.2 million GB seconds. Okay, so now provision concurrency charges will be 7.2 GB seconds multiplied by 0.504167. Okay, so this is the default provision value. Okay, and that comes around $30. And next we have to calculate the request charges. So the monthly request price is 0.20 per 1 million requests. Okay, and the monthly request charges will be now 1.2 million. That actually is the number of times it has run multiplied by 0.20. Okay, that is a charge. So you will get $0.24. Okay, so the compute price is 0.00, that's 509722 per GV seconds. And the total compute duration for seconds is 1.2 million into 1 second. So it ran 1.2 million times for 1 second each. So it becomes 1.2 million seconds. And the total compute GB seconds is 1.2 million seconds multiplied by 1024, that is the amount that is allocated, by 1024, that is we are converting it to GB, so 1.2 million GB seconds. Now the total compute charges will be 1.2 million GB seconds multiplied by this value. This is what we get from the duration, which comes around $11.67. So now the total charges will be provision concurrency charges plus request charges plus compute charges. So the total price that we had for provision concurrency charges was $30, and now for the request charges we have 0.24, and for the compute charges we have 11.67. So total it comes around 41.91. So let's suppose you allocate 1024 MB to your function and enable provision concurrency on it for 2 hours. The concurrency that you configured was 1000. You executed the function 1.2 million times during the 2 hours and ran it for 1 second each. Then you will be charged for $41.91. So before moving forward, I want to tell you that please make sure you are aware of AWS Cloudfront and how it works. And if you need some clarifications, then please watch the video by clicking the info icon on the top right corner. I have provided the link there. But if you are already aware of AWS Cloudfront, then let's move ahead. So just to start off this discussion, let's first understand that Lambda is regionally scoped. And if your users are in another different regions or other different regions, then to provide users with a better user experience, you should take help from another service that can help you execute your code closer to your users. And that service is AWS Cloudfront. And that's where we place our AWS Lambda at Edge. And remember one thing, AWS Lambda at Edge is a feature of AWS Cloudfront or Amazon Cloudfront. So remember this very carefully, that it's a feature of Amazon Cloudfront and not a feature of AWS Lambda, which basically lets us to run our code closer to our users of our applications, which actually improves performance and reduces the latency that we actually want to reduce. So to summarize it, AWS Lambda at Edge is a provisional feature by Amazon Cloudfront that helps us to run or execute our code closer to our customers that can help us reduce latency and increase performance. But don't think that you won't get the same features as AWS Lambda. For sure you will. Yes, with AWS Lambda as well, you don't have to provision or manage infrastructure in multiple locations around the world, and that's a very good thing. And just like you have trigger points with AWS Lambda, when it comes to AWS Lambda at Edge, it runs your code in response to events that are generated by the Amazon Cloudfront. So that is our content delivery network, or the CDN. Okay, so remember this very carefully. So it runs your code in response to events that are generated by the Amazon Cloudfront. Okay, so now let's discuss some of the features of AWS Lambda at Edge. And some of them might be similar to what we have already discussed for AWS Lambda, so don't worry about that. So the first one is build more responsive applications. So what AWS tells us is that with AWS Lambda at Edge, you can run your code globally at AWS locations close to your customers and users. So you can deliver full-featured customized content with high performance and low latency. So for example, your users are present in Germany. So you can provide the users in Germany the content in their own language, or you can provide them the content that is more relevant to their region. And the second one is no servers to manage. So with AWS Lambda at Edge as well, we can automatically scale our application code or the function code we have, and we can run our code at AWS locations around the world. And the best part is that you can do this without having to provision, scale, or manage origin servers at those regions and locations. And obviously you don't need to set up any load balancing or any DNS. The third one is important, and it is relevant to AWS Cloudfront for Lambda at Edge. So that is customize your content delivery. So if you remember Amazon Cloudfront, we used to set up our CDNs in regions, and we used to cache the resources of the origin server, which used to help the users located thousands of miles away to access these resources with low latency and improvised performance. And that data that we get as a part of the request or from Cloudfront can be customized using AWS Lambda at Edge. So that is what we discussed a few moments before, as you can deliver full-featured customized content with high performance and low latency. Okay, so the incoming request that you have can be customized with AWS Lambda at Edge. So we have already seen how Lambda works. Now let's see how Lambda at Edge works. So in simple words, the first step is for you to write the code that you have and upload it to AWS Lambda as a part of your Lambda function. Then we create a trigger point at AWS Cloudfront to execute our Lambda code. And then we have our Lambda at Edge run our code closer to our customers and users, and you pay for the compute charges. Okay, so it's pretty simple, straightforward. And here, if you see the image below, if you have used Cloudfront at the end of the form, while you're creating a CDN distribution, AWS actually provides us an option to choose the Lambda ARN to which you're going to provide or for which you're going to provision for AWS Lambda at Edge. And there are multiple events with which you can associate your Lambda code, like your viewer request or viewer response or origin request or origin response. And that is what we will be discussing now. So when you create a Cloudfront distribution, if you go to the form and if you go down below at the end, you will have Lambda function associations. There you can choose one of the Cloudfront events and you can provide the Lambda function ARN, and that will actually help Cloudfront to trigger your Lambda at Edge code. Okay. So here we will be discussing about how and what are the Cloudfront events that can trigger a Lambda function. So recall the image I showed you in the previous slide about the events and think of them as the trigger points. If I ask you how does a trigger point gets invoked, you might tell me that if I click a link, if that is associated with a REST API or a HTTP API, then it can help us trigger an API gateway event. Yes, it's obviously right. And if you ask me about what about SNS events, then yes, with SNS, it will be based on if there are messages that can act as a trigger point. So the first one that you see here, the example that I gave, that was indirectly manual event where you're clicking on a link to trigger the event. And the second one or the other one is an automated event, isn't it? So there are two types of events that we can have. When we talk about Cloudfront, here we have to think of events as incoming requests or outgoing responses or vice versa. And having said that, remember very carefully that there are 4 events here. So first one is viewer request, the second one is viewer response, the third one is origin request, and the fourth one is origin response. So viewer here is the user itself, And the origin is the one who is serving the request, isn't it? And here as well, if you see, there are 2 incoming events and there are 2 outgoing events in the example that I've shown below. And if you see here, the CloudFront actually sits in between you and your origin server. And now let's see how these 4 trigger points work and how we can invoke our Lambda at edge using these 4 trigger points. Okay, so the first one is viewer request, and that is the incoming request to the CloudFront, and it triggers Lambda after CloudFront receives a request from the user. Okay, and before executing the code, it actually checks to see whether the requested object is in the CloudFront cache or not. So it's simple. The user actually sends the request and the CloudFront checks if it is already there before sending it to the origin. So the second one that you see here is origin request. That is the outgoing request from the CloudFront, and it triggers the Lambda code before CloudFront forwards the request to the origin. Okay, so if you see here, it's just before the origin and it has to pass through the CloudFront. Okay, so it triggers the Lambda code before CloudFront forwards the request to the origin. So that is why it is called as origins request. And the third one is the origins response. So that is an incoming response from the origin, and it triggers the Lambda code after CloudFront receives the response from the origin. So the response has been received by the origin to the CloudFront. And if this is a response from the origin, the function gets executed even if there are any errors that are returned from the origin. And there are 2 conditions when it doesn't execute the Lambda code. So the first condition is when the requested file is in the CloudFront cache and is not expired. So that is the first condition. And the second condition that you have to remember is when the response is generated from a function that was triggered by an origin request event. Okay. At last, the fourth one is the viewer response. So that is an outgoing response. So here it triggers the Lambda code before CloudFront actually forwards the response to the viewer. So the important part here is that the function executes regardless of whether the file is already there in the CloudFront cache, because it is an outgoing response to the viewer. And moreover, it has been explicitly triggered as a part of the event set by the developer itself. And the function doesn't get executed in these following cases that you have. So the first one is when the origin returns an HTTP status code of 400 or higher, and when a custom error page is returned, or when the response is generated from a function that was triggered by a viewer request event, or when CloudFront automatically redirects an HTTP request to HTTPS. So it's basically when the value of the viewer protocol policy is redirected from HTTP to HTTPS. And you might ask me, can I use the same function with multiple distributions or multiple CloudFront distributions? And you might ask me if I can use the same function as multiple CloudFront distributions. And the answer will be yes, you can use them. And you might ask me if CloudFront actually waits before making a trigger when an event is already in progress. And the answer will be yes, it does wait for an event to complete, post which it can make another trigger. And you might ask, like, can I have all these events for a single function? And the answer to this is also yes, you can have all these functions, you can have all these associations to a single function. So try to understand this very carefully, because it will be very important when you will be designing applications for your users who are going to use it across the globe. Okay, so I hope this was clear. Let's move on. So now let's check some of the use cases. So first use case is to simplify and reduce origin infrastructure. So we can use it for website security and privacy, where we can use it as a combination of AWS S3, CloudFront, and AWS Lambda at edge. And we can create dynamic web applications at the edge by using AWS S3 plus AWS CloudFront along with AWS Lambda at edge and DynamoDB. With this 4 combination, we can create a very good dynamic website. And we can use it for search engine optimizations for SEOs. And we can also use it to intelligently route across origins and data centers. And we can use it for bot migrations at the edge. And the second use case that we have is for improved user experience. So we can get real-time image transformation, and we can perform A to B or A or B testing. And we can also perform user authentication and authorization, and also for user prioritization and for user tracking and analytics. So now let's check out some application design with AWS Lambda at edge. So let's discuss the first design for AWS Lambda at edge, and if you get time, you can also try this. So requirement for this application is to provide dynamic content to the users across several regions, and thus reducing the latency and improving the overall user experience. First off, for the user interface, we have a static HTML code that we have placed it in the S3 bucket. And for the CDN or the content delivery, we have hosted the CDN in the US region, which is configured with AWS Lambda at Edge, which has our code that pulls the data from the DynamoDB, which helps us to format our website page with the desired dynamic content that we want to serve the users of North America. So with Cloudfront, the biggest advantage is that the content gets cached at the edge locations, and the next time the user actually asks for the content, if it is already present in the edge cache, it doesn't have to query the same from the origin. Okay, so it makes it very easy and very quick for the users to access it once it has already been queried. So this is a simple design for an application to be hosted along with Cloudfront and Lambda at Edge. Let's move on to the next one. With Lambda at Edge, we have another use case that can be discussed, that is the intelligent routing across origins and data centers. I know you might feel that S3 is a global service, and why are we using S3 as an example? That's right, but having said that, if you have ever created an S3 bucket, you will know that even though the S3 service is global, you have to assign a region while creating the bucket. So don't get confused with this. Okay. The service itself might be global, but the presence of data should be within the region itself. Okay, I hope all of you are aware of GDPR guidelines, and that's totally a different topic. And if you want, you can just read about the GDPR guidelines. Okay, so let's move on. So what we have here are two buckets of our static code. One is hosted at S3 in Europe, and the other one is at S3 in North America. When the user is using the website, it needs to have faster access, and this can also be done by using our Lambda at Edge to compute the route to the local region and its origin, which is closest to the user. And that is the main purpose of using Lambda at Edge here. Okay. And this is the feature by which we can intelligently route across origins and data centers. So here, when the user visits the website pythaholic.com, the application here makes an HTTP request to the Cloudfront Edge location, and it triggers the call to the AWS Lambda at Edge, which actually computes the location or route based on the user's location, and then helps the views to be redirected to the nearest origin. But you might ask me, like, can't we do this with Cloudfront alone? Why should we use Lambda at Edge? Yes, you are right. We can also do the same by editing the Cloudfront configuration to use a different origin when you want to move your origin from one region to another. But the main disadvantage here will be CDN or Cloudfront. It will take a lot of time for the CDN to propagate across the globe. So it will be a failure if there are frequent changes. So that is the reason why we are using Lambda at Edge. So here, Lambda function resolves a DNS record containing the origin that should be used. Thus, it is quick to switch between origins, and you don't need to edit any Cloudfront distribution configurations here. So that is a very big yes from the AWS side and from my side as well. And the best part is that the same Lambda function can be used by multiple cloud distributions as well, or Cloudfront distributions as well. So that's an added advantage here. And there are many such use cases actually for AWS Lambda at Edge. Okay, so now let's talk about the pricing model that we have for AWS Lambda at Edge. The first and foremost thing that you need to remember is that at this point in time, as per the documentation, there is no free tier for Lambda at Edge. So at this point of time, it's a big no-no for anyone who wants to use it for free. But yeah, if you can spend some money, then you can as well do the demo. Not a problem with that. And the changes are applicable to you on the basis of the number of requests executed across your functions. And the charges are applicable to you on the basis of the total number of requests executed across all your functions. And Lambda at Edge counts a request each time it starts executing in response to the Cloudfront event globally. Okay, so the Cloudfront event is most of the trigger points that we discussed, and the request pricing is $0.60 per 1 million request, and that turns out to be 6 zeros, then a 6 per request. So that many dollars actually you have to pay, and the duration is calculated from the time your code begins executing until it returns or otherwise terminates. So let's take an example here. So if you allocate 128 MB of memory available per execution with your Lambda at Edge function, and if your Lambda at Edge function executes 10 million times in 1 month and it runs for 50 milliseconds each time, your charges would be as per the following. Okay, so if you calculate 128 MB of your memory that is available per execution with your Lambda at Edge, then the duration charges will be 0.00050625125 for every 128 MB second used. Okay, how do we calculate this? So if you see 1 GB second is 0.405001, and if I want to calculate what is the cost of 1 MB second, then I have to divide it by 1024. So I got the value as 0.0007 actually 4883. And if I have to calculate 128 MB, then obviously I have to multiply that with 128. So this is the value that I get, 0.50625125. That is what we are actually keeping it here as well. As there is no free tier for Lambda at Edge, you have to pay this if you are going to use this use case for your demo. So the monthly compute charges will be, so you have the monthly compute charge, that is 0.0000625.125 per 128 MB second. So total compute will be 10 million times it has run. So 10 million into 0.05. So we are converting it into seconds. So because we have 50 millisecond, so we wanted to convert it into seconds. So we have converted that, and it becomes 0.05 seconds. So if you multiply 10 million with 0.05 seconds, then obviously you get 500,000 seconds. I'm explaining you basic maths, but I think you already know this. So now the monthly compute charges will be 500,000 seconds multiplied by the number of the amount that you actually pay for 128 MB seconds. Okay, so that comes around $33.13. And the monthly request charges will be, if you see, the monthly request charges that you have is 0.60 per 1 million request. So as it has ran for 10 million times in 1 month, then you have to just multiply 10 million into 0.6. That turns out to be $6. So now the total monthly charges will be obviously monthly compute charges plus monthly request charges. So that comes around $3.13 plus $6, that is 9.13 per month. Okay, so now if you allocate 128 MB of memory, okay, at your Lambda at Edge function, and if your Lambda at Edge function actually executes 10 million times in 1 month and it ran for 50 milliseconds each time, then you will have to pay $9.13 per month. So this is how it has been calculated, and you can go to the documentation and read about the pricing model for all the other regions that we have. I hope you got the point with this example of how we actually calculate the price for Lambda at Edge. Let's move on. Okay, so that was a really good feeling to complete AWS Lambda and AWS Lambda at Edge. But wait, there is still more to come. The next service that we will be discussing is API Gateway, and by far API Gateways is one of the most requested service. So I'll try and simplify it as much as possible for anyone to understand. And yes, I haven't forgotten the demo. I will be doing a demo after AWS API Gateway, so where we will be hosting a website with Amazon S3, AWS API Gateways, and AWS Lambda, so that we can get the complete picture of how they are being used in tandem with each other. But before starting with AWS API Gateways, I'm sure most of you already know what are APIs and what are gateways, but there might be a few members who may not have come across these terms. So for our friends who aren't aware of what are APIs and gateways, I'll be explaining these topics with visualization here so that they have a better understanding of the topic or the concept that we have for APIs. So if you're already aware of APIs and why we use them, and if you don't want to listen to this, then you can skip to the portion where we actually start discussing about AWS API gateways. I have mentioned the timelines in the description as well, but if you want to join us, then you're most welcome. So let's start off by understanding what is an API, or what is an application programming interface. And I won't ask you to define these terms for me, and I won't tell you some definitions either. So now let's together understand what is an API. So let's go back to the days where it was all simple and you were in charge of doing everything that you wanted to do. Without technology at your fingertips and services to be consumed, the best option was to do things manually. For example, if I wanted to book a pickup truck, I would go to the store, that is a pickup agency, to talk to the service provider, and I would book the pickup truck. And if I had to apply for a credit card or a debit card, I would go to the bank and take the card application form and fill it and apply for a new card. And as well, if I wanted to get a new pair of shoes, or if I wanted to buy any trousers or t-shirts, I would surely hop up to the nearest shopping center and get the things that I want. So now let's take an example of a real world scenario where we want to book a pickup truck, as we want to shift all the items to a new home. So the best option for us is to go to the pickup service and talk to the manager that we have. So here is our user. So this is our truck, this is our truck owner, this is the pickup service center manager. And the next thing will be to place the order for the pickup truck based on the information that we need to provide to the manager, like the place of delivery, time, the pickup date, and the address. And now your request is well received at the store, and he tells you that, sure sir, please let me check the details and I'll get back to you with the confirmation. So he then calls up to the truck owner to ask if he has a truck available. Based on his response to the order request, he either will confirm or reject the request. Okay, if he doesn't have it, then he'll surely reject it, but if he does have it, then he will surely accept the request. Mostly in these cases, the requester actually would inform him to schedule it as per the availability of the vehicle, and that is how you book a pickup truck. Okay, so if the condition is satisfied, you will get the information back and you will let them know that whether the booking has been confirmed or not. Okay, so now let's see what happened when things actually changed. Things and people started migrating towards application and websites that could provide them with the same service at the reach of their fingertips or just a click away from their desktop and laptops. So they got a form where they could fill in the details of what type of service they want and then make the booking. And based on the availability of the truck, it would automatically let them know if their booking was successful and the amount they were supposed to be charged with. In the form, you would get all the information that you should fill in order to make the request, starting from the name, date of pickup, address, and the type of truck that you need. That is, it might be a mini truck or a large one. And when you clicked on the submit button, it would fly the request into the servers and get you the result back. And the best part is, it wasn't limited to that. And now it is so powerful enough is to draw information from not just one agency or service provider, but from several more, who can actually deliver the same service for far better prices and tariffs compared to the one with whom you were connected for a longer time. So the next time you try and click the submit button, the application compares the prices of the agencies which provides the service, and we find that agency A is giving us the cheapest price. So we select that and place the order. And that's how the magic actually happened. We started off by speaking to 3 people and doing the manual work to get our booking done, to a single application which gave us a chart of prices to compare, and we were able to book the pickup truck sitting at home with the most reasonable price. And this was all possible by the help of the APIs, or what we call as application programming interfaces. For every communication that you see here, from the user to the application, from the application to the form, from the form to the user clicking on the order button, from that to the backend servers of all the agencies that we have, and the response back to the applications from the servers. All that you see here is the magic of APIs. Now with the help of APIs, you can book a pickup truck, apply for a credit card, and shop online with just a few clicks. And all of this is possible today with APIs, and the way we are able to communicate with services using APIs. I don't want you to think of answers just yet, but keep thinking of all the possibilities that we have when we use APIs. Now you have seen these examples, and I would want to ask you, what do you feel has made it really special? Yes, it's communication. And that is what has throttled our ways of sending and receiving data and information. With APIs, you are not just talking to the application, but also with the services and databases. The operating system that you use currently, the mouse click on the media player on your laptop, the touch of the Spotify app on your phone to access songs. All this is brought to you by the magic of APIs. So API, or the short form of what we call the application programming interface, is a software mediator that allows 2 applications to talk to each other. So the application is basically a software program which is designed for the specific use case, and when 2 programs wants to communicate, they want an interface through which they can talk to each other, isn't it? So when 2 programs actually want to communicate, they would want to have an interface through which they can talk to each other. The user here using the application is trying to communicate with the server of the agency which provides the service, and the communication that you see here is based on the request made by the user and the response given by the server. And the way we talk is basically using our APIs. But you might ask me why we call it as an interface. So I'll give you a small example and you will surely be able to relate to that. If you're using your phone right now and you see all those buttons and tabs which help you navigate through your apps and settings, those are basically an interface. More precisely, it's called as user interface or user experience interface. So the user wants to talk to the application and it needs a medium to interact. So it has a user interface. Else you would still be typing commands of ls, dir, mkdir and copycon and cat to read your files. Similarly, services and apps need a medium to communicate, and that's your APIs. The simple visual here tells us how the API request flow and how the response comes back to the user. It's all about the request that has been sent and the response that has been received. I hope you're already starting to get the hang of what APIs are. Let's move on. So when you write your applications that might have a lot of information that could be shared or what could be reused, right from the database that you have or the method or function or the source that you currently have as a part of your application. And as I've already explained before about a well-architected application, all the code and functionality will be written in a way that it can be later reused by other applications or developers. So in this case, if other programs or developers want to make use of these services and want to make use of this data that you have, then the programs have to talk to the applications using the APIs provided by the application itself, that is basically provided by you, and the API can provide them with the necessary information that they need. For example, if you want to get the details for the number of products or prices that a certain category of product has on Amazon or any other shopping website, you need to use the APIs to access it. And those APIs will be given to the developers by Amazon itself. And another very important example can be cited here is if you want to create an account on social media website, you basically go to the website and get it done using its user interface. Okay, but if you want to do that programmatically, then you will need the APIs from the social media application so that you can write the code to make the API call and create the account. Okay, so in this way, applications and the developers are able to communicate with each other and use their feature by using the APIs. And this is how we actually integrate applications together by using the APIs. And when we talk about application integration, so the next time when you think of using a service provided by other application and you wish to integrate it in your program or software, think of APIs. APIs are everywhere now. Talk about Instagram, talk about GitHub, talk about YouTube or even Twitter. When you need the information on how to use the features of these applications in your application, make sure you check the APIs. Now, as we've already discussed before, API or application programming interface is a medium or a software mediator which helps two applications to communicate with each other. You need to understand that an application that is written with proper standards is always divided into multiple spheres or services or functions or methods. And the developers would never want to write the same service or same code again. And if that service can be used by another application, they would basically host the service and expose the API so the other application that we have can make use of it. And thus make it public for programmers so that it can be used across the world. And there can be multiple ways we have APIs for, like we have the HTTP API, which is the Hypertext Transfer Protocol API. I'm sure you're aware of the OSI reference model and the layers that we have. So HTTP works on the application layer. So anything that you access on the World Wide Web comes from the fact that the data is being propagated with the HTTP API. And the next one is the REST API or RESTful API, and this is also a form of API that is probably the most widely used API in the world. The REST APIs also make use of the HTTP APIs and protocols, but they adhere to a certain principle of methods and resources. Okay, so remember this very carefully. REST APIs, methods and resources. Okay, like the way they send the data and how they make the call. So they depend on methods and resources on the way they actually send the data and make the call. And the most commonly used methods are get, post, put, delete, mostly forming the set of CRUD operations that you can perform. So you might ask me, what is the difference between HTTP API and REST API? Yes, that's a very valid question. So I won't go deep into this, but remember one thing, HTTP APIs are the communication channel and they work on the HTTP protocol, and they aren't bound by any particularly single rule of how they should send the data across the internet. They can be or they may not be, but any API that uses HTTP as a communication channel is an HTTP API. Okay, REST as well. But REST is representational state transfer API, and it depends on the response of the request to determine the state of the resource. So I hope you remember, as I told, like REST depends on methods and resources. And when you think about REST, when we call it as a representational state transfer API, it depends on the response of the request to determine the state of the resource. So if the resource that you have does not exist, then it has to wait for the response of the request, and it will determine the state of the resource based on the response received. So here you can as well say that all REST APIs are HTTP APIs, but all HTTP APIs may not be REST APIs. And the method in REST APIs are precisely English verbs which help a user or developer to exactly understand the purpose of the API. And actually that clears the confusion, isn't it? So if you have get, then you know that it is used to read the response from a particular resource. And if it is post, then you know it is used to create a new resource. Okay, in that way. And there is another one that we have here, the WebSocket APIs. So WebSocket APIs work on the transport layer, and they are a bit different than the HTTP or REST APIs. On one side, the REST APIs are one-way communication and are based on the request response or client-server theory. Here, TCP is a full duplex two-way communication channel, where unlike HTTP or REST, we don't actually wait for the client request or the server's response. Here, the client and the server talk independently to each other over a single TCP connection. So remember this very carefully, that WebSocket APIs work on the TCP protocol, and TCP is a full duplex two-way communication channel, where unlike HTTP or REST, we actually don't wait for a client's request or a server's response. Here the client and server actually can talk independently to each other over a single TCP connection. And you might think why I have taken only these three APIs into the discussion. Actually, because AWS API Gateway lets us create, manage and secure these three APIs by using the API Gateway. Don't worry, I'll make a video on the OSI reference model and I will explain to you how these protocols and layers work. But for now, please just remember these points. So when we talk about HTTP APIs, as we have discussed before as well, that it's a client-server request-response model. And if you see here, the client or the user we have here makes a request by hitting a URL on the browser. And then what happens next? Obviously, the page gets loaded on his or her screen, isn't it, if he obviously has an internet connection. And there might be various types of data that the website can have, like it can be music files, or there can be image files, or that could be some video files as well. And remember that all this data that is being propagated is over the HTTP protocol. Okay, so the images, the content that you see on the web pages that you have are basically using the HTTP. And with the REST APIs, we have our clients work with the API calls made over the HTTP protocol using the HTTP methods like get, post, put, delete, patch. And they work on the request body templates with XML or JSON or HTTP calls. And the simple CRUD operations are as shown as below here in the example. So the get actually is used to receive or read a particular resource. The post is basically used to create a new entry or a resource. And put is basically used to update an existing resource, and delete, obviously it is used to delete an existing resource, and patch, it is used to update a resource, but it does not need all the payload to be provided in the call. It is, you can consider this as a partial update. And to make REST calls, you can use SDKs or the software development kits or Postman or REST clients to call or execute any REST APIs. But mostly when we are working on programming languages like Python or Java, we make use of the SDKs provided by the application itself so that we can make the request calls to the APIs and get the work done. And the third one we have is the WebSocket API. As I have already mentioned before, TCP is a full duplex two-way communication channel where, unlike HTTP or REST, we don't wait for the client's request or the server's response. Here the client and the server talk independently to each other over a single TCP connection. So in WebSockets, you have the connection open request, which is completed with the initial handshake that you see here. And then when the connection is open, you can send bidirectional messages, which will be persistent over the connection. And here, if any of the parties actually close the connection, it actually ends or closes the communication channel. Okay, so each of the parties have a right to actually close the connection, and in that sense it actually closes the communication channel as well. So I hope you got a shorthand idea of what API is. Let's move on. So now that you're aware that API is the way two applications or programs actually communicate with each other, so what should be a gateway then? Isn't it? As mentioned here, it's an opening that can be closed by a gate, and in computing terms it is a device used to connect two different networks, especially a connection to the internet. But I think these two options don't make much sense, isn't it? So I'll give you an example. Listen to this very carefully. It would be actually highly relatable to you as well, I think. So imagine your friend wants to come to your home to collect some books. He knocks at your door, and then you open the door and you allow him in, and then you hand him the book that he wanted, and your friend actually leaves the house, and then you close the door. Now I would ask you to replace your friend to be the API call or the network call, your friend's house to be a public network, and your home or your house to be a private network. Then your house door is the gateway, which allows public access to your private network space. So if I ask you, if you never opened the door for your friend, would he be able to get inside? No, the answer will be no, isn't it? He will never be able to get inside if you never opened the door for him. So tell me, what is a gateway? So it's a node that acts as a gate or doorway between two networks. Having said that, just for now, please don't combine both APIs and gateways together to form the API gateways. Have some patience, we'll have discussion on this very shortly. So now let's design a simple web application based on the pickup truck architecture that we had, and let's understand what could be the possible actions that we can have with REST APIs. So a traditional web service or web application has a user interface, isn't it? And the URL resource for the actions that we want to perform on the application. And each functionality has been divided into multiple microservices. So we have the login service, the inventory, the user data, and we also have the booking service, and for the transaction we have the payment service and the report generator as well. And for the overall data storage we have the database service as well, and these microservices are written in Python and are hosted as a part of the deployment on the local server. And we have all the REST APIs to perform the necessary actions and handle the request. So we have the post call where it actually creates the login for us, and then we have a post call where it actually creates the request. Then we have a put where it actually updates the job ID. Then we have a delete which actually deletes the job ID, and we have a get where it actually gets the report for us, like /pickup/update123 being the job ID /reports. There is one more get for us to actually retrieve the data, like get pickup update /123/data. Okay, so if suppose I have booked the truck and I just want to see the information, this API will be used to actually access the data that I have for that particular request that I have made. Okay, and if we transition the same to AWS, we host our services on our EC2 instances and we shift the database to EC2 as well. In both the cases, it fits the requirement as these are well-to-do services and they are effectively managed. And the developers have written all the code to provide us with the APIs, and they will keep on writing code and upgrade the frameworks to show that they are very hardworking and they are compliant to the standards of REST API services. Everything is very good. But what if I tell you that these services and API endpoints can be simplified to an extent that you only have to tweak them once in a while to manage the API and the services, and they will take care of themselves? Would you believe that? If not, think again. I wasn't bluffing. I was serious when I said we will change all of that with a single entity, and that's our AWS API gateway. And that is how we will change it. So now the developers write the code for the API in AWS Lambda or EC2 or wherever possible. We create our API endpoints at API gateway, which acts as our trigger points to communicate with the backend services that we have as a part of our Lambda or EC2 code. The user actually doesn't have to access the Lambda or EC2 directly. It can straight away make calls to the API at the API gateway and get the response back. It is as simple as it can get. No need to write additional code for the URL resource routing, and you have your API endpoints. It's that simple. And now we have replaced all the get, put, post methods that we had previously with the APIs at API gateway, and it will work the same way it did before, but it has been upgraded to be more resilient and tolerant. Ignore my parrot in the background. And that's where we start off with AWS API gateways. Finally, we are here to talk about API gateways. So API gateway is a fully managed service that makes it easy for developers to create, publish, maintain, monitor, and secure APIs at any scale. It may not be your conventional gateway, but sometimes you might think, why is it called an API gateway? So as I mentioned before, this service also sits in between your users and your services for all the API requests like HTTP API, REST API, and TCP APIs as well. Okay, so now let's get some more details about API gateways. So AWS API Gateways is one of the most important service of AWS with respect to the exam and to your journey as an AWS user or developer or architect. So if you get time, please read the documentations as well. And moving on, with AWS API Gateway, you get an interface with AWS to create your own APIs without writing any additional code. And you can securely publish them so that it gets exposed for the users to consume. You can maintain the state or the version of the APIs as well, and you can as well monitor the traffic or the load and the way it's performing using the tools that are given by API Gateway. So API Gateway is a managed service, as it is already written here, and it is a managed service by AWS, so feel free to use them as per your needs. You don't have to maintain anything for API Gateway, you pay only for what you consume. And with API Gateway, you can create HTTP APIs, RESTful APIs using HTTP, and WebSocket APIs as well. So now you got the point. Why did I stress on these three types of APIs? So API Gateway also supports containerized and serverless workloads, and it supports web applications as well. So if you are using ECS to host your application, then also you can make use of API Gateway. And API gateways have other provisions as well for traffic management, for cache support, authorization and access control, performance throttling, traffic monitoring, and API version management as well. And with API Gateway, there are no minimum fees or startup cost. You pay for the API calls you receive and the amount of data transferred. So remember this very carefully. API Gateway is like a reverse proxy. So if you know what reverse proxy is, you will be aware that reverse proxy acts as a resource provider for the client, but it makes it feel like it has come from the source itself or from the origin itself. And that is why in API Gateway, you pay for the API calls you receive and for the amount of data transferred out. Okay, because it is an API service. You have hosted APIs, so whenever a user or a developer or an application consumes your API, that is the amount of money that you're going to pay. When we think of API gateways, we need to understand that we are thinking of an entity that helps two applications to communicate or talk to each other based on the request and response cycle that we have. So when we consider the type of resources that can be used or that can make use of API Gateway, we have a vast range of resources and technologies that can work with API gateways for the communication and data processing. The first one that you see here is our private application, which could either be hosted on our private VPC or as well in our on-premise solution, and can make use of the APIs that is published at API gateways, actually to communicate with the application backend or services that are hosted on a VPC or on-premise. And next, when we talk about the IoT devices, the log stream data and the analytics data is really important for them, and they can make use of these application servers hosted behind the API gateways that can execute their request and process critical information. The same goes with the web application and mobile and streaming applications, which make use of AWS Kinesis for data streaming. And these applications can also be configured using API gateways when they are working with AWS Lambda or DynamoDB and other services that can help them easily set up their application and be worry free about the throttling issues, because API gateway will be handling that. And there is one more very important feature that API gateway provides is API gateway caching. You can cache your API responses with a TTL. You heard it right. Yes, we can cache the response of the API in the gateway cache for a period of time so that it can be faster to access for the users. And the foremost thing that you have to remember is that with API gateways, you create API endpoints. And these endpoints will be accessed by your customers or developers or users to bind with their applications. Or basically what we can say is integrating it with their applications. So imagine you're working on these applications and you have a provision to create your APIs and put your code on the AWS EC2 instances or AWS Lambda, or have your data stored at AWS DynamoDB, and later on being able to access these functionalities that can help you process the data that you have or help you get the data that you need with just a simple API. Wouldn't that be great? So before moving on, I want to tell you once again that think of API gateways as a simple front door for the applications to access data, business logic, or functionality from your backend services, which can be at EC2 or Lambda or any other web application. Now let's talk about some of the benefits of using API gateways. So the first one that we have is efficient API development. With API gateway, you can run multiple versions of the same API simultaneously, which actually allows you to quickly iterate, test, and release new versions. So if you have worked with REST APIs, you will know that we version APIs for testing new features or any changes that we have or we make to the APIs. But most importantly is that with API changes with like payload or interface changes, these changes should be informed to the users before you make them live, because their existing integrations will break in case there are interface changes. That would seriously be disastrous if the production code failed for the users because of your mistake that you did not inform them. So as a best practice, we version the API so that we can test the new features and make sure they are stable, and we share the new version with the customers, keeping the older versions alive so that they make the decision when to migrate it to the newer version of the APIs. So this whole process becomes very safe and convenient with API gateways because you can run multiple versions of the same API simultaneously, which allows you to quickly iterate, test, and release new versions. So the second one that we have here is performance at any scale. Another very good feature is that API gateways work along with the AWS Cloudfront to provide the lowest possible latency for API requests by using the global networks at edge locations. May your resources be anywhere in the world, you will get the best experience when it comes to accessing resources like APIs. And the third one is cost saving at scale. So here as well, you only pay when your APIs are in use, that is when they are being requested for, and there are no minimum fees or upfront commitments. And for HTTP APIs and REST APIs, you pay only for the API calls you receive and the amount of data transferred out. And API request prices are as low as $0.90 per million requests at the highest tier. And we will discuss about the pricing model later on. So for now, just remember this. And the last one that we have here is flexible security controls and easy monitoring. For security, you can provision authority or what we also call as authorized access to the APIs with AWS Identity and Access Management and AWS Cognito or Amazon Cognito. And using AWS CloudWatch, you can visually monitor calls to your service and measure the traffic and its performance or peak level activities. Okay, so I hope that was clear. Let's move on. So now let's check some of the use cases for API gateways. So with API gateways, we can create HTTP APIs, as we all know that by now. This actually enables us to create more powerful RESTful API services, which will cost us way less than creating REST APIs. So I know there is a slight confusion that hit your mind just right now that what I just said create more powerful RESTful API services, which will cost us way less than creating REST APIs. So I know you will ask me, you said two things here, RESTful and REST APIs, but both are same, isn't it? The thing is, it depends. So REST is representational state transfer, and that's basically in simple forms a architecture. which actually follows strict guidelines. Like it is stateless, it uses one and only one protocol, that is HTTP, and it performs CRUD operations using URLs, and should obviously talk or communicate using JSON and XML. But RESTful API services are the ones that actually follow these principles very strictly. So with AWS API gateways, we can create HTTP APIs which enable you to create RESTful APIs with low latency and lower cost than REST API. So you can create HTTP APIs by which you can send requests to AWS Lambda functions, which can get you the data that you need, or to any publicly accessible or publicly routable HTTP endpoint. And with AWS API Gateway, you get the support for OpenID Connect and OAuth 2.0 authorization, and it has built-in CORS. So now that you've created an API using API Gateway, so the thing that you need to understand is that with API, we have HTTP methods that perform a certain CRUD operation. And every API method like get, post, put, update, delete will have a corresponding function attached to it. So if you make a get API, then there will be a function attached to the get request. And if you have a post call, then there will be a function that will perform the action that is made to be performed using the post call. Okay, so when we design APIs with Lambda using API Gateway, we create a function in Lambda and map an API to that function. Okay, so you create a function and map or associate a API with that function. So whenever you call that API, it indirectly calls that function for you. So when we design API with Lambda using API Gateway, we create a function in Lambda and map an API to that function. So when a user calls that API, it executes the function that's written in AWS Lambda. And the HTTP API has two parts. One is the method and the other one is the resource. Okay, so I hope that was clear. Let's see the cycle of API and Lambda function. So we have our client here that is here to make the request, and here the operations are divided into four parts. And the first part is the method request. That is very obvious. So here it defines the parameters and the request body that an application developer must send as a part of the request to access the backend through the API. This is basically your public interface because that is coming from outside to the API gateway. So it acts as a public interface. So that's basically your method request. The second part is the integration request. So after you have received the request, in this part you map the body of a route request or the parameters and the body of the method request to the formats required by the backend. So you will change it and map it according to what the backend needs. So before it reaches to execute the code, we actually format the request body here. Okay, and the third part is integration response. So after we have processed the API call and the request, we need to format it again as a part of the response for our clients by mapping the status code, headers and payloads that are received from the backend. And you have to understand here that for the response to be sent back to the client, it has to be formatted in a specific way so that it can accept the response. And last but not the least, the fourth one that we have is the method response. Here, this acts as a public interface because it is going to communicate with the client, and which defines the status code like 200 or 400 or 500 and the headers and the body that a developer should expect in response from the API. So let's suppose you are expecting that to be in a particular format, then it has to be formatted in that particular way before it has to be sent to the client. So the two methods that you see here, which are public facing, that are method request and method response, they are the public interfaces, and the integration request and response that you see here are internal interfaces. So when you make an API call to the AWS Lambda function sitting behind your API, it follows the pattern that we just saw here. So I hope that was clear. Let's move on. So as we have already discussed before that we can also create WebSocket API, and with WebSocket API, remember that the client and the server can both send messages to each other. So there is no one directional communication, it's a bidirectional communication channel that gets created with WebSocket, and until the connection is open, you can send messages to each other. And we can create serverless applications with WebSockets like chat applications and like real-time dashboards such as stock tickers, so which updates the stock values in real time, and real-time alerts and notifications as well. By using AWS X-rays, you can trace messages and the patterns that they have as they travel through the APIs to the backend services, more like Wireshark. And lastly, you can easily integrate your WebSocket APIs with HTTP, HTTPS endpoints. So let's understand this better with a simple example here. Okay, wait, at first you might think that it's same as what we have seen before with other web applications. But the difference here is we will do this with WebSocket APIs, and let's see how. Okay, so think of this as a food delivery app, and you have placed your order, but once you have received the food order, you found that the portion of food and its quantity was not satisfactory. Okay, so the next thing that you would do is, or the next thing that you did was, you went on to the food delivery app and you clicked on help, and it opened the chat window, and then it asked you what was the issue, and it gave you the options to reply. Okay, I know you are trying to insinuate or trying to relate it with a very famous food delivery app. Just hold on to that. So okay, so you choose the food was not satisfactory, the portions were very less. Then again, the application asked you with options as to which item did you have problems with. You chose item 1, and then it asked you like would you like a refund. Then you chose yes, and then you closed the application and came back again to answer the question within a few seconds. And you saw that the application is asking if you can close the chat and if you could provide the feedback. So as in when you clicked on yes, close it, what the application did is it immediately closed the chat, and there was no longer an option for you to type or any option to reply. I know most of you might have done this with Chiggy or Tomato or Uber Eats or other food delivery apps, and that's what we are doing here as well, but with using the WebSocket APIs. So you might ask me, why are we using WebSocket APIs? So let us understand this. Okay, so a chat window is basically a bidirectional communication. Okay, so when a user A opens the chat window, it sends the event to the API gateway to establish a single WebSocket connection. To establish a single WebSocket connection to the API gateway from the device. Once you have the connection, after which the event goes back to the Lambda function along with the metadata and payload and the connection ID of the device, which then gets stored onto the DynamoDB to make sure the connection ID can be later on used for communication. And as I already said, that the Lambda function stores the data to the Dynamo database, as I already mentioned before, and then based on the message event, the next Lambda function generates the appropriate message based on the chat script that you have written, like the next response for the user, which is like your virtual chatbot. So then the message is sent back to the user using the API gateway. And the next time it sends the message, the application again checks for the metadata and the connection ID, based on which it accepts the message and keeps it alive. So if you close the chat or you have accepted the closure, then your connection closes. And that moment as well, the Lambda function gets triggered to clean the data that your connection ID provided, so that the next messages or the subsequent messages doesn't have to be delivered as the connection is already closed by the user. Okay. And the next time you open your chat window, it again checks for the connection ID based on the authentication that you have, and you repeat the cycle once again. And in this way, you are able to serve so many customers at once. And the connection closure can also happen with the application as well. If you don't respond for a longer period of time, if there is a timeout that is set by the application itself, it will close the connection automatically from the application side. Okay, I hope it was clear enough. If you felt it was a bit confusing, please listen to this once again. Your concepts will be cleared, and if you want me to create a chatbot using WebSocket API, please put that in the comment section below so that I know that you would like to see it in real time. Okay, so let's move on. So now next up is who uses API gateways, or who actually wants to use API gateways. So logically, even if you didn't read the documentation, you would have already got the idea that if this is a AWS API gateway service, you will be either on the side of people who actually create the APIs, or else you will be on the side of people who are actually using these APIs, isn't it? So yes, so we have two kind of developers that we have here who uses API gateways. So one is the API developers who actually create the API, and the app developers who actually consume these APIs. Okay, but there are a few requirements of these as well. So let's compare them one by one. So API developers create and deploy an API to enable the required functionality, and you must be an IAM user in the AWS account that owns the API. So when you think of creating an API using API gateway, remember these points. And moving on to the app developers. So if you are an app developer, you are mostly responsible to build the functionality or build the functioning application to call AWS services by invoking a WebSocket or REST API created by an API developer. And you are the actual customer of the API developer, but you don't need an AWS account to access the API, provided that the API doesn't either require IAM permission or supports authorization. Okay, and for the app developers, you can make use of the identity providers as well, which are a lot available in the market, right, which includes Amazon Cognito User Pool or Facebook or Google. So we have already done a lot of praising for API gateways, so let's do some more and let's check some of the most important features of API gateways. Okay, so let's do a recap on things we need to remember. So the first thing is you can create RESTful APIs using either HTTP API or REST APIs, and by creating HTTP API you can serve for both serverless workloads and HTTP backends, and you can have up to 71% cost saving and 60% latency reduction. And by creating REST APIs, you can have API proxy functionality and API management in a single solution, and you don't need to manage them separately. And with WebSocket API, you can create bidirectional communication channel using the WebSocket API, and you can create serverless applications using Lambda and DynamoDB. And you can route requests through private resources in your VPC. If you have any service in your private VPC, you can also create a connection to that. And you can also build APIs for services that are sitting behind private ALBs, private NLBs, and IP-based services registered in AWS Cloud Map. And a very important feature is that you can manage traffic to your backend systems by allowing you to set a throttling rule based on the number of requests per second for each HTTP method in your API. Okay, so with that, you can use it as a load balancer as well, but for your API requests only. Okay, and you can also set up a cache with customizable keys and time to live in seconds for your API data, as we have already discussed before. And you can create custom APIs for your code in AWS Lambda and then call the Lambda code for your API. Let's suppose you want a certain custom URL, or you want to create a custom URL for your region, then you can do that as well. And you can also integrate API gateways with AWS Step Functions, AWS Elastic Beanstalk, and Amazon EC2. And with CloudWatch integration, API Gateway actually provides you with a dashboard, monitor calls to the services, and you can get real-time data about the performance matrix of the API calls, latency and error rates. Okay, so further enhancing the security, you can create API keys on API Gateway and set access permissions on each API key, so that you have the control of who can access the APIs and what level of actions they can perform. And last but not the least, a very important one that we have already discussed before, you can run multiple versions of the same API simultaneously, so that applications can continue to call previous API versions even after the version or the latest version has been published. I think this we have already discussed before, and it is a very important point. So I hope that was clear. Let's move on. So now let's discuss the pricing for API gateways. So for free tier people, there is plenty of good news here. So API gateway includes for free tier of 1 million API calls received for REST APIs. And for WebSocket APIs, we have 1 million messages and 750,000 connection minutes for the WebSocket APIs per month. That is for up to 12 months. So to understand the pricing better, we need to check this table here. So the column here represents three entities: HTTP API calls, REST API calls, and WebSocket APIs, which is termed to be the messages. On the left row header, we have the number of requests per month and the price per million. So for each API type, we will be checking the amount charged in a month per million. So the page is right here. You can pause the video and check it as well. But one thing you have to remember here is that the more your request calls are, in the long run, you pay less. Okay, so if you see here, for HTTP API, we pay $1. So we pay $1 for the first 300 million. And then we pay only $0.90 post 300 million request. So it becomes affordable on the scale. And there are a few AWS advisories based on the security that we have for AWS API gateways. So let's check them one by one. So what they tell is, like, always use multi-factor authentication or MFA with each account, and we must use SSL TLS to communicate with the AWS resources, and we must make use of AWS CloudTrail to set up API and user activity logging, and along with using default encryption that AWS provides, like CMK or other encryption mechanism. For encryption at rest, if you choose to enable caching for a REST API, you can enable cache encryption as well. And for encryption at transit, API gateways don't support unencrypted HTTP endpoints. The APIs that are created with Amazon API Gateway expose HTTPS endpoints only. and API gateway doesn't support unencrypted HTTP endpoints. Okay, so you can create private REST APIs that can be accessed only from your virtual private cloud. So it's a very good option to quickly set up application APIs that are supposed to be private between your on-premise and the cloud. Okay, and for logging and monitoring, you can use these AWS services like Amazon CloudWatch Logs, Amazon CloudWatch Alarms. And for debugging, you can enable Kinesis Data Firehose to actually log API calls. And you can as well use AWS CloudTrail and AWS X-Ray and AWS Config. And out of these, the AWS CloudTrail is very important because it can keep track of which user or role or an AWS service has performed what operations. And that can be very helpful in case someone actually deletes any data and actually runs away. No, sorry, just joking. But yeah, it can help you with the audit. Okay, isn't it? So now this is the last thing, the 5 rules of thumb for API gateways. So first rule is implement least privilege access. Okay, I know if you are already aware of IAM, you already know about least privilege access. So give minimum access to the users at the start. Okay, and increase their privileges as and when the requirement increases. Okay, and implement logging as always, and implement Amazon CloudWatch alarms, and enable AWS CloudTrail, and always enable AWS Config. Okay, so these are the 5 rules of thumb for API gateways, and these are the rules that you must remember when you are going to create APIs using API gateways. Hello everyone and welcome back to the channel. In the last session we discussed in length about API gateways, and at the end I told you that we will be having a hands-on demo for API gateways in the next session. But to spice things up, why not design a small and a simple service that will help us understand API gateways and AWS Lambda in a better way, isn't it? So today we will work on a small project where we will understand how we can use AWS API gateways along with AWS Lambda to fetch our data from AWS S3. So if you're ready, let's begin. But before moving forward to the AWS console, let's understand the requirements here. So initially our users at team A were uploading files to AWS S3 bucket, and the users at team B used to download or use them directly from the bucket. Post which there was a requirement that all the data that the users are going to download should be base 64 encoded. So we made a design change, and for the base 64 encoding we introduced a simple Lambda function. And to provide the users a bit of convenience, we thought of providing them with an API endpoint resource so that they can pull the data they need. So now let's check out how we can get this done. So for the first step that we are going to do is basically having a AWS S3 bucket. So if you have already created a bucket, then it is well and good, you can use the same thing. So I'll just go ahead and click on S3, that is a service that we are going to use, the S3 bucket. So just click on S3, or you can just type here as well S3, and you can use it. Okay, so here you can just click on S3. And I have a lot of buckets already in my S3 store. So I'm going to use this bucket, my new web bucket. And there are a lot of files here that are already available to me. So I can use any of these to simulate the scenario that we are having, like we are trying to download these files. So what happens, I will be uploading files to this bucket that I have, and you also can create your own buckets, not a problem. Okay, so this is the first resource that we want. So we are done with the S3 part. Okay, so the next thing that we wanted to do was we wanted to create a Lambda function, isn't it? So let's go to Lambda. So for that, you can just click on the services and just type Lambda, and you will get the service drop down there. So you can just click on Lambda here. So as I've already created a function before, so it is showing me the direct page where all the functions are listed. But if you are new and if you haven't created any Lambda functions, you will be shown with this page. Okay, so this is the one that will be shown to you. So here there is a very beautiful demo that actually Lambda provides, and I want you guys to check that out as well. So the first thing that you read here is AWS Lambda, and the next thing is lets you run code without thinking about servers, and that is the most important and the beautiful aspect of using Lambda. And you pay only for the compute time that you consume. There is no charge when your code is not running. With Lambda, you can run code for virtually any type of applications or backend service, all with zero administration. Okay, so let's see how it works. So here is a simple demo that we can run. So I'm going to use Python because I know a bit of Python, so not a problem with that. So you can use any of the languages that you are familiar with. So here is a Lambda handler. Actually, basically this is the function that is going to be executed, and by default, and by logic, it should return hello from Lambda, isn't it? So I'll just run it. Okay, so it printed hello from Lambda, isn't it? So we did not create any instances here, or we did not install any Python packages here to run this code. We just wrote the code here and it executed for us, and that's how we got the result. And that's the convenience of using serverless. Okay, so next is how actually Lambda responds to events. So if you click on this, you will see there are so many events that Lambda can process information for. Okay, so there is a mobile phone where we can get the mobile IoT backend data. So if you click on this, the message passes through the mobile or IoT backends, and here is the streaming data, or it can be from the Kinesis or any message broker that you have, or here it is the file. It can be from your S3 bucket that is being processed with the data that you have. And here the Lambda actually is taking streams of data from everywhere and it is trying to process it, isn't it? So whenever the application stream or the data flow increases, it basically scales up automatically. As you can see, when I'm clicking on it repeatedly, it just scales automatically, because the number of input is getting increased every time when I'm clicking on it. See, you can see it is increasing the number of instances or the background processing power that it has whenever the traffic increases. Okay, so next is basically here you can see that Lambda responds to events. Once you create Lambda functions, you can configure them to respond to events from a variety of sources. Try sending a mobile notification, stream data to Lambda, or place a photo in the S3 bucket. Okay, so that is what it is trying to tell you, as what we have already discussed now. So the next thing is basically to see how it scales seamlessly. So this is the number of invocations that you have, and this is the price that you're going to pay. Okay, so let's suppose I am going to continuously click on streaming analysis, and let's see how much the cost is going to increase for us. See, when I'm trying to increase by sending it a lot of input, see, after 1 million requests or invocation, the price has increased. Okay, and let's suppose I keep on pushing the data here. But if you see, gradually with higher amount of invocations, you see the cost becomes highly reasonable. So that is why Amazon Lambda is considered to be a highly effective processing power that we need. So here also what you've seen is Lambda scales up and down automatically to handle your workloads, and you don't pay anything when your code isn't running. So your first 1 million requests or 400,000 GB seconds of compute per month are free. I think we have discussed in length about the pricing model for Lambda, so I don't think so we can discuss it anymore. You can just go ahead and read them in the documentation. Okay, so the next thing that we have here is to create the function itself. Okay, so let's click on create function. And here I'm not going to use a blueprint or any serverless app repository. I'll just create it from scratch. Okay, and I'll give my function a name. So my function's name can be anything like
my S3 function -new, or I can just give a demo. Okay.
So here I'm going to use Python 3.7. Okay, and there is a permission levels also you can add, where you can add the execution rules that you want. So the one that I'm going to use is basically S3, because I want execution rules for S3. So there are three options here. You can create a new role with basic Lambda permissions, or you can use the existing role, or you can create a new role from AWS policy templates. Okay, if you click on create a new role from AWS policy templates, it means that either you don't have an existing policy or you have a separate requirement for your new function that you're creating. Okay, so here I'm just going to create a new role. So click on this and give it a name. So I'm just going to copy this, and I'm just giving I'll just give it a name as -role. Okay, here I want to use Amazon S3, so I'll just use Amazon S3 object read only permission, and if you don't find it, just type S3 and you will get both of them. Okay, so you can just use object read only permissions for now, and if suppose you want a delete permission or anything, you can explicitly do that from IAM as well, but I'll be using this one for now. So you can just click on this because we are going to read the S3 objects, isn't it? So this is the permission that I need for now, and what we have done right now, we have selected the author from scratch. We have given the function name. I have given the runtime, that is the language that I want to use, that is Python 3.7. The permission type that I want, this create a new role from AWS policy templates, and here I have given the template as Amazon S3 object read only permissions. Okay, so the next thing is create function. Okay, so now your function is created. Okay, so successfully created the function my S3 function demo. Now you can change its code and configuration to invoke your function with the test event, choose test. Okay, so now what we have to do is we have to just move around this form, and I'll explain you some of the things that are important to us. Okay, so this thing that you see here is a designer. You can actually add trigger points or you can add destinations to this, and you can create a workflow here as well. So once you click on add triggers, you can see from which all services you can trigger AWS Lambda. See, you have so many services like API Gateway, AWS IoT, Alexa Skills Kit, or application load balancer. You can also invoke it from the application load balancers, or CloudWatch, Code Commit, DynamoDB, Kinesis, S3, SNS, SQS, and there are so many other integrations that you can have. Okay, so when you select one of them, you can add them as a trigger point from which you are going to trigger this function. Okay, and there is one more thing called destination. So here we have the destination types as SNS topic, SQS queue, Lambda functions, or event bridge. Okay, and you can choose what type of source it will be. Like it will be will it be a asynchronous invocation or it will be a stream invocation. Okay, and here there is one more condition that you can add, whether your function invocation or the destination invocation will be based on whether your function has failed or on success. Okay, so these are a few things that you can also do it, but for now I'll just focus on the task at hand. And this is basically your IDE for writing your Lambda function. It has all the details, and here if you see that if you want to use any Python libraries explicitly that are not available by default with Python, you have to create a package and you have to upload it to Lambda. So that is one more thing that we will do later on, but that's not required as of now. So you have this function, and this is the Lambda handler. So when you create a Lambda function, you actually specify a handler, which is the function in your code that AWS Lambda can invoke when the service executes your code. So if you see, AWS function or the AWS Lambda functions will have Lambda handlers as the function within which you write your code. So as you see here, we have the AWS Lambda handler. So this is the function Lambda handler within which we will write our code. And the Lambda handler function actually takes two parameters in normal cases. That is, first one is event and the other one is context. So event parameter is used to pass event data to your handlers. So this is mostly like a dictionary, but you can also pass list, string, integer, or none types as well. You might ask, why is it different? Because the trigger points are different. So you might think like, why is it like different based on like a dictionary or a string or a list? So some might send string data, some might send integer data, or some might send JSON. So it depends on the trigger points on how the Lambda handler actually receives the data as a part of its input. So like for example, it can come from Cognito, or it can come from API Gateway, or it can come from Amazon Lex or Kinesis, anything for that matter, which can act as a trigger, isn't it? So, and the context is used as a parameter that actually provides the runtime information to your handler. It's like passing the context object. And one of the context method is get remaining time in milliseconds, which returns number of milliseconds left before the execution times out. So similarly, we have methods like AWS _request _ID, which can get you the request ID for the execution. There's a list of methods that you can have with context. You can read them in the documentation as well. So now that you have a good idea of what are events and contexts, let's move on. So to execute this program, what you have to do is you have to just click on test. Okay, so here you have to configure a test event. So you can just give an event name here, my event name or something of your choice. Okay, these are by default parameters that you're going to pass, and then you can just click on create. So it has created an event name test event. Okay, so you can just click on this and you can start the test. Okay, so now the response has been received as status code is 200 and hello from Lambda. So this is the thing that actually we have returned when we executed the Lambda handler. Okay, so now you must understand a few things here. So let's suppose I want to show you something. So import time. Okay, I'll just type import time and I'll just give here time dot sleep of 5. Okay, and let us just save this and let's run the test. See, so now it failed. As you can see here, task timed out after 3 seconds. Why did it happen here? Like if you see here, go here as well in the execution details, you will find that it has timed out. This is because the default setting that you have here, the basic setting that you have here, if you edit on this portion, you will see the default timeout that has been set is 3 seconds. So you have to increase it to, it can depend on what your requirements are. I'll just increase it to 3 minutes. Okay. And you can just save it. Okay. So the next time when you're trying to execute it and it times out, come here and then try to execute this. Okay. So if I just click on test once again, it should not fail for me, even if I have increased the time of execution to 5 seconds. See, now it has passed again. Okay, so it's a bit simple, isn't it? We are going to see like how actually we are getting the logs generated here. So if you go here, this is the summary that you have. This is the request ID. This actually what I was saying, right? AWS request ID. You can print this as well using a context. And here you also can print the memory use 128 MB. Okay, or the max memory used. Okay, and here if you see, we are getting the log outputs, isn't it? So here if you see, we have the CloudWatch log group. If you click here, okay, so here once you come here to CloudWatch, you can see here, if you see, the log group has already been created, that is /AWS/Lambda/my-s3 function demo, and for this we can have the logs generated. Okay, so if you click here, you can see the logs have been generated. Okay, so these are the logs that have been generated. But how did they get generated? Because we have given them the permission that comes by default. So if you click on permissions, you can see we have Amazon CloudWatch logs. And what are the resource and action that it can take? So it can take 3 actions, or it can perform 3 actions, and it can execute 2 resources. Okay, so what are the resources it can execute? So it can create log groups, it can create log streams, and it can put log events. So it can create the log group here, and the log streams that you see here, it can create this log stream, and it can put the data as well. Okay, and it can put the logs as well. Okay, so 3 operations. And by actions, so it can create log groups, create log streams, and create log events. Okay, so by actions and by resource. So these are the 2 resources. So the next thing that we wanted to do was we wanted to pull the information or the data that we have from our S3 bucket, isn't it? So go back to the S3. So we have this S3 bucket right now where we have the data, and this is the Lambda function that we have created right now. So we have to write the code now to pull the data from the S3, isn't it? So let's do that. So this is the bucket that I wanted to access the data from. So I'll click on this, and it is inside Pythoholic. So I already have a sample text 01. So that is what I'll be using to extract the data from. So for this, I'll be using the Boto3 module, and I'll tell you like how it exactly works. So for now, we don't need this code. So you can just delete this, and I'll start typing the code. Okay. So first thing that we have to do is we have to import the Boto3 module, and then I want to import JSON to format the response that I have. So S3 is equal to, so if you want to perform any operation, you have to call the Boto3 module dot client. So which client you want to use? So we are currently using S3. So I'll just type S3. Okay. And the next thing that we want to create the Lambda handler. Isn't it? And the parameters that we need is event, comma, context. Okay. So these are the two things that we need now. So now we need the bucket information. So the bucket that I have is my-new-web-bucket, and the key is basically the path that I have. So Pythoholic / I'll give sample01.txt. Okay, so this is the path that I have now. This is the key that I want to access. So if you go here, so this is inside Pythoholic. So Python/Pythoholic / sample01. So you can add the path. If your file is inside this directory itself, you can just provide the file name, okay, or the data that you want. So next thing is to fetch the data that we have. So there is a module called s3.get_object, okay, that you can use to basically fetch the data from the S3. So that is what we'll do right now. So try, and here I'll write the data pull code. So s3.get_object of, we have to pass two parameters here. So the first one is bucket, which will be equal to bucket, comma, we need key equal to key. Okay, so that's it. There's the method that you're going to use to pull the data, get_object, and we already have the permission added to read files from S3, so don't worry about that. And the next thing is JSON_data is equal to data of, so this is the body parameters that we have, the body data that I have. So it will be body dot read. Okay, I have to close the except exception as E and print E. Okay, so I hope the code is done now, so I can just save it and I'll just execute it. Test. Okay, so byte says no, okay, I cannot do this, so I'll just remove this, not a problem. I was thinking it will be some, yeah, see, so I have the data now. Okay, so I'll create a new file and I'll just add this disclaimer content and I'll just save it in desktop. So this will be our next file, so I can just keep it as sample02.txt. okay, so now I have saved this, and on S3 I can just go ahead and upload it, upload a file, add file, then sample02. okay, then just click on upload. So now you see sample02.txt, and here when I go back and I just change it to 02 and save it and I test it, I should get the data. Okay, so I got the data here. Okay, so not a problem. So now this looks pretty simple. We have got the data from the S3 bucket that we have, but this doesn't add up. This is not what we wanted to do, isn't it? So the next thing is, the one that we wanted to do was, our users are wanting us to have base 64 encoded data, and for that we actually created the Lambda function and we wanted to give them the API gateway. Okay, so now that is what we'll do. We'll integrate API gateway to this. So to integrate API gateway, what we can do is we can precisely add a trigger here. So you can just click on this add trigger. This can also be done through API gateway itself. If you go to API gateway and try to integrate the Lambda function, that also is fine. You can do that. Okay, so now just create a API gateway trigger point. Okay, so we'll create a new API. So it will be a new REST API. So I'll have a REST API now. So you can just provide IAM as the security and just click on add. And there are additional settings that you can give, but I'm not going to give it right now. So just click on add. So once you've clicked on add, you can see the topology has been changed. So now the trigger point that we have is API gateway. So whenever any REST invocation is done from API gateway based on the function that I have, it will basically call the Lambda function that we have here. Okay, so now let's go to this invocation that we have. Okay, so here in AWS API gateways, we will start off by invoking the Lambda function that we have from our trigger point that we have, that is API gateway. Okay, so the first thing that we did was we had uploaded the file that we need on S3. Then we created a Lambda function where we actually wrote the code that actually fetches us the data from the AWS S3 bucket. So now we have to add the trigger point, and here we are going to create a REST API. If you see here, the API gateway has been created, and this is basically any request that you want to send. But for our specific purpose, we are going to create a method. So that will be our get method, isn't it? So just click on actions and then click on get and then click on yes. Okay, so now the invocation will be from the Lambda function. So this is the integration type. So integrate with the Lambda function, just click on this one and don't select Lambda proxy as of now. And your Lambda region is basically AP South 1, and you have to provide the function name, isn't it? So go back here and you can copy this function name and you can provide it here and just save it. You are about to give API gateway permissions to invoke your Lambda function. Yes, that is what we want. So click on OK. So now it has been saved. So your get API is now created. So if you see here, we have 4 methods that we have already discussed before. I hope you remember that. So method request, integration request, the Lambda function, my S3 function demo, integration response, and the method response. Okay, so now click on test. So if you see here, we have query strings that we can pass. We have the header values that we can pass, which actually has application JSON, as you can have like a header that you can pass from here. But the main thing that we want to check here is basically by clicking on test and seeing whether it is able to invoke or not. Okay, so click on test. Okay, so you now are getting the response. So this response is coming from your Lambda function. Okay, so that is 200, and that is the disclaimer that you get. This is a disclaimer. Actually, this is not a disclaimer, but the text actually which we have uploaded, isn't it? So that is from our Lambda function. And here what it is doing is it is trying to execute this particular file, and it is trying to fetch this particular file from this bucket. Okay, but this is not that interesting because this is hard coded, isn't it? We don't want that. We want our users to have the capability of passing the bucket name and the key value so that they can get any type of data that they want, or any data or any file that they want from the AWS bucket, isn't it? S3 bucket, isn't it? So that is what we will do right now. Okay, so now we have to change some things in both the places. So I'll just go ahead and tell you what we are going to change here. So you see here, these are the two bucket and the key parameters, isn't it? That is what we are trying to make it dynamic. So the event type that you see here, we'll configure the test event again, and here we are going to pass the bucket. sample02.txt, isn't it? So these were the inputs that we wanted to give to our function. So now you can just save this. Okay, I'll just remove this, save it. Okay, there was a comma, so I'm sorry for that. So now what happens is, as I had already told you, that the event actually can help you get the parameter values. Okay, so that is what we are going to fetch it from. Okay, we'll remove this, and event of that will be a dictionary, isn't it? So how we are going to access data from the dictionary? We are going to use the key. Okay, so event of bucket, and this will be obviously event of key. Okay, so now this has become dynamic. You can just save it, and let's go back to the API gateway and let's see whether we are going to get the result or not. Click on test. See, because we don't have the keys that it needs. Okay, so now we see the real test here. Okay, so now if you just click on test now, it will just pass on the values that the input has. So if you go here to configure, these are the inputs that are currently being passed. So from the API gateway, we're not getting the inputs anymore. Okay, so this is the problem right now that we have. So what do we need? We need these values to come to the event from the API gateway. So that is what we'll do right now. I'll just click on test once again to show you like, yeah, it works here. Okay, so now the function actually works individually, but for it to work from API gateway, we need to do some modifications, and that is what we will see now. So go back to method execution and go back to method request. Okay, so what do we need now? We need query string parameters, isn't it? So they will be bucket. Okay, so these are the query parameters that we are going to pass, and that will be our key. Okay, and you have to create the validation, and you have to just check on these two checkboxes to create the validation. Here it is telling that we have clicked on these two, but our request validator is still not validating these parameters. So you see here request validator, and there is a pencil icon here. You can just click on this and you can select verify query string parameters and headers. Okay, and that's it. Okay, so you have added the request validator and the two query string parameters. Okay, so you can just click on method execution now, paste it here, and let us see whether we are able to execute the code or not. No, still we are not able to execute it. Okay, so what is the problem now? So the method actually is getting the value that it needs, the bucket and the key, but the integration request, actually the data that has to be formatted for this functionality to receive, or the function to receive, we haven't done that. Okay, so click on request in integration, and here if you come back to this point here where we have the mapping templates, you can just click on this, and here we don't have any templates as of now. Okay, so now if you click on this add mapping template, I have to tell the content type to be application/JSON, because the content that I'm trying to pass on as a parameter is basically our JSON itself. Okay, so application/JSON, you can just type application/JSON and click on create. Yes, your current pass-through behavior will pass all request payloads directly to the endpoint without transformation unless there is a match for the incoming content type. Do you want to secure this integration to only allow requests that match one of your defined content types? Yes, I want it to be application/JSON, isn't it? So now we have given that it is application JSON, but what type of JSON we want? We want to capture the parameters and we want to send it to the function that we have, isn't it? So first we collect the information from the user, from the request parameters that we have or the query parameters that we have, and we have to then pass it on to the function itself. So we have to add the template as well. Okay, so the template goes like this. So you can also use template that you want based on your requirements that you have. So this is a basic JSON template that we have, where you can just pass the bucket as your input parameters. I'll just use this, don't worry about it, it will work just fine. If you have any doubts, you can just let me know. And the second one is keys. Okay, so you have to just provide the same way that you have provided for the bucket. Input dot param of key. Okay, and this is the format that our function is going to expect the data from. So now just close the bracket. So we have the bucket here, the input param of bucket, and key is basically input param of key. Sorry, params. Sorry, it's params. Okay, so now just what you need to do is you need to just click on save. Okay, and then go back to the function that you have, the get request that you have. Okay, now click on test. So now we have the function here, my function demo, and this is the parameters that I want to pass. Let's see whether we are able to run this or not. Click on test. See, now what we have done, we have passed the inputs that we wanted to have from our query parameters, that is bucket equal to my new web bucket, and the key that I have passed is Pythoholic /sample02.txt. So this is very interesting because now we have the data here in the S3 bucket, we have the functionality here, and we have the access point or the resource here. But what we wanted to do, we wanted to actually have the base64 encoding, isn't it? So let's modify our Lambda function to pass on the base64. Okay, so now there are slight changes that we have to make here to the part of the code that we need. So the first thing is we have to import base64. Okay, so this module has been imported now. This comes by default, so we don't have to worry about that. And the next thing that we have to do is we have to format the JSON data that we are getting into base64. So base64 underscore bytes equal to base64 dot, what is the method name? That is b64 encode. So we are going to encode it. And what are we going to encode? We are going to encode the JSON data, isn't it? So now that we have encoded the JSON data, what we are going to do, we are going to pass it. Okay. So once we have this, we have to just pass the data here. Okay, that's it. So now we have encoded the data that we wanted to encode, and now the next thing that we want to do is we are just going to pass it, isn't it? Just now. So now just save this and let's see the magic. See, now I'm getting the string here, but it is telling unable to marshal response. It is not able to parse that. Not a problem. I'll pass on the string itself. Okay, encoded string. See. Okay, so now you have the data back. So this is the encoded data. So now everything is complete. So our users are able to upload the data to S3. User team B actually is able to access it from the API gateway, which actually is taking the data from AWS Lambda, which is in turn picking up the data from the Amazon S3 and converting it to base64 and then passing it on as a response to the users. Okay, so this was a very simple example on how we can integrate AWS S3 and AWS Lambda and AWS API gateways as a trigger point to our AWS Lambda. Okay, so I wanted to make this demo so that we can cover both the aspects of API gateways and AWS Lambda, but mostly the problem that people face is around having or passing the inputs to the Lambda function that is from the REST APIs by using the parameters. So that is the point that I wanted to cover in this demo so that you don't have to face any challenges with that. And I could have done this with simple code execution, but we have to do something different, isn't it? I hope it was fun and it was exciting for you guys to learn as well, as it was fun for me to actually design this and to do this demo. So I'll meet you in the next one. That's for AWS VPCs. And until then, it's Pythoholic signing off.